Hi everyone and welcome to this course. My name is Martin Yanev, a professional software engineer and a computer science professor at Fitchburg State University. In the next few hours, I will show you how to create engaging and interactive games using C# and Unity. This course is very suitable for beginners that want to jump in game development and start with the very basics. In the first section of this course, we're going to learn about player movement, game physics, AI, and user interface. Then I will show you how to use Unity-specific tools such as input stream, animator, navmesh, as well as I will show you how to integrate audio into your games, visual effects, and organization techniques. The idea is that by the end of this course, you're going to be able to build completely 2D and 3D games by yourself. By the way, you're also going to be able to access the full code that we will cover in this course from the GitHub repository that I will link in the description. Now make sure that you like this video and subscribe my channel for more similar videos like this one. And now let's get started.
In this video, we're diving into the exciting world of Unity, particularly focusing on exploring the Unity editor. Unity is an incredibly powerful game development platform, and understanding its interface is crucial for bringing your creative ideas to life. We are going to start from scratch, beginning with how to create a new project. Starting a new project in the Unity Hub is the first step in your game development journey. With Unity Hub, you have a centralized management tool for all your projects. To get going, you will see a button labeled New Project prominently displayed. Click on that and a new window will pop up, giving you options to customize your new project. You'll need to select an editor version. If you're a beginner, I'd recommend picking one of the long-term support LTS versions. These versions are stable and receive constant updates, making your experience smoother. Next, you'll see a variety of templates from which to choose. For beginners, I recommend opting for the 3D car template, as it sets you up with the essential tools you need to start your adventure in 3D game development. Make sure to name your project and select a location on your hard drive that has plenty of space. Trust me, games can quickly eat up storage. Once you've done that, click the Create Project button. Now, you might need to grab some popcorn because Unity might take a minute to set everything up for the first run. But don't worry, future launches will be much quicker. Now that we've set up a new project, let's unpack the Unity editor. The first thing you'll notice upon launching the editor is its layout. Unity provides a range of customizable windows that serve different purposes like the hierarchy, scene view, game view, inspector, and project windows. Let's start with the hierarchy panel. This is where all your scene objects live. It organizes them into a parent-child structure that helps you manage your scene efficiently. Imagine you're building a city. Your building's child objects belong to the district parent object. Moving on to the scene view, this is your primary workspace. Here is where you'll manipulate game objects directly and design your environments. It's like your artist's canvas where you can paint with your 3D assets. The game view, on the other hand, lets you preview the game in real time. Think of it as a camera that captures how your game will look when it's running. Now let's take a moment to appreciate the inspector window. Whenever you select an object in the hierarchy, the inspector shows you all of its properties. Want to change the color of an object or add a new component to a game object? You do that through the inspector. If you can change it, you'll find it here. Lastly, there's the project window. This is where you can manage all your assets, textures, models, sounds, scripts, the works. You can organize your assets into folders just like in a file system, which is essential as your project grows. Speaking of scripts, let's jump into how to create your first C# script in Unity. Scripts are the backbone of your game. They dictate the logic and interactivity. To kick things off, you'll first want to create a scripts folder in your project window. Right-click in the Assets area, select Create, then choose Folder and label it Scripts. It's a good practice to keep your code organized. Next, let's go ahead and create a new C# script. Right-click the Scripts folder, select Create, and then C# script. You might want to name it something fun like My First Script. Now let's implement a simple line of code inside the start method to make our script interactive. This method is called at the beginning of the game's execution, making it the perfect place to initiate actions. The line we are adding is debug log hello Unity. This command sends a message to Unity's console window, which is invaluable for debugging and feedback on what your code is doing. When the game begins, this statement triggers, and the console outputs the greeting hello Unity. Seeing this message confirms that your script is functioning properly, making it a great tool for verifying that your code executes as expected. This is a fundamental practice in game development, as it reinforces the connection between code and its results in the game environment. By using debug log, you can track your code's behavior, ensuring any logic you develop works seamlessly. After writing this line, don't forget to save your script and return to Unity, where we'll next attach it to a game object and see our code come to life. Now let's see how we can implement conditional logic using an if-then statement to enhance the interactivity of our game. In the code snippet, we check if the player's score surpasses a value of 100. If this condition holds true, the game responds by executing the action inside the curly braces, which in this case is to log a congratulatory message to the console. This ability to evaluate conditions dynamically allows us to create responsive gameplay scenarios. For example, we can motivate players by providing feedback based on their performance, such as celebrating high scores. Moreover, using such conditions facilitates complex decision-making in the game logic, making our games feel more alive and engaging. As you develop your game, think about various thresholds or states that could yield exciting player interactions. By encapsulating these behaviors in simple conditional statements, you empower players with a more personalized gaming experience that reacts to their achievements, ensuring they feel rewarded for their progress. This type of programming not only keeps your code organized, but also enhances the overall gameplay experience. Now let's see how we can implement a method for player movement in Unity. This code defines a public method called movePlayer that takes a single parameter, speed, which represents the movement speed of the player. Inside the method, we utilize the transform component of the game object to move it forward in the 3D space. The key part of this line is the transform translate function, which takes a vector as its input. Here, we're creating a movement vector by multiplying vector 3 forward, which points in the forward direction, by the speed parameter and time delta time. The use of time delta time is crucial as it ensures the movement is smooth and consistent regardless of the frame rate. It accounts for the time elapsed between the current frame and the lost, ensuring that the player moves at the desired speed over time. This method not only helps keep our code organized and modular, but also enables us to reuse it easily in different parts of our game. By controlling the player's movement through this dedicated method, we enhance the clarity and maintainability of our scripts, making it easier to implement complex behaviors as our game evolves. Finally, let's touch on the importance of managing asset imports in Unity. Assets are crucial since they supply the art, sound, and support materials in your game. When importing, be aware of the format and the settings to ensure optimal game performance. In the project window, you can drag and drop files directly into Unity, but remember to organize them. Keep your materials, textures, and scripts sorted into folders. For example, think of a clean wardrobe. Keeping similar items together helps you find what you need quickly. Moreover, make use of the console window for feedback. This window is a developer's best friend, logging errors, warnings, and prints from your scripts as you work in real time. Learn to interpret what it tells you. This can save you hours of debugging later. The Unity editor empowers creators to develop rich, immersive experiences with its core functionalities. By understanding its components from navigation to scripting, you establish a solid foundation for your game development journey. So, get your hands dirty in that editor and start creating something incredible. Now let's see how we can create and utilize a character class. In our example, we define a character class that encapsulates two key properties, name and health, The name field is a string that holds the character's identity, while health is an integer representing their vitality in the game. To simulate damage taken by the character, we implement a method called takeDamage, which accepts an integer parameter denoting the amount of damage. When this method is called, it subtracts the damage value from the character's health and outputs a message to the console, detailing the damage taken and the remaining health. This approach neatly bundles related properties and methods into a single unit, exemplifying the principles of object-oriented programming. Next, we'll expand this concept by implementing a simple game manager that instantiates a character object. In this game manager, we will create an instance of our character, assign it a name and an initial health value, and simulate taking damage to observe how our method responds in action. This will not only reinforce our understanding of class functionality, but also demonstrate how to manage game object states efficiently using C. Now let's see how we can implement the Game Manager class to manage our character instances effectively. In this example, we define the Game Manager, which inherits from MonoBehavior, making it compatible with Unity's event-driven architecture. Inside this class, we declare a private variable called Player, which will be our instance of the character class. Next, we focus on the start method, a crucial entry point where we prepare our game state when the scene loads. Here, we create a new instance of the character class, naming it Player, and set its properties. The player's name is assigned as Hero, and we initialize the health to 100, giving our character some vitality. After setting up the player's attributes, we utilize debug log to display a message in the Unity console, confirming that our player has entered the game along with their health points. Following this, we simulate gameplay by calling the takeDamage method, where the player loses 20 health points. This showcases how we can organize code to handle character states and actions, emphasizing the benefits of using classes for maintainable and scalable code in game development. Now let's see how we can extend our character class by implementing a player class that introduces additional features. In this code snippet, we create a player class that inherits from the character class, allowing it to utilize all the properties and methods defined in the base class. Specifically, we add a new public field for weapon, which represents the weapon the player wields. To demonstrate the player's action, we implement an attack method within the player class. This method outputs a message to the console that indicates the player is attacking with their equipped weapon, showcasing how we can add unique behaviors while leveraging inherited functionality. Next, let's see how we can instantiate this player class in our game manager. Here, we create an object named Player1, assigning it a name, health, and chosen weapon. After setting these values, we log a message that confirms the player's entry into the game, including their health status and weapon. We then call both the attack method, highlighting the player's unique action, and the takeDamage method, inherited from the character class, showcasing how inheritance enables us to manage interactions efficiently. Now let's implement the following enemy class to enhance our game. This class inherits from the character class, allowing it to reuse properties like name and health. In addition to these inherited features, we introduce a new method called Flee, which gives enemies the ability to escape during gameplay, enhancing their behavior and making encounters more dynamic. Next, we override the takeDamage method inherited from character to add custom logic specific to enemies. This implementation logs damage taken, updates the health variable, and checks if the enemy's health has dropped to 0 or below. If it has, we log a message indicating that the enemy has been defeated, showcasing how we can modify behavior based on the enemy's state. Now let's see how we can use this enemy class in our game manager. We create an instance of enemy, but declare it as a type of character. This is a demonstration of polymorphism, where we can treat derived classes as their base class while still accessing their specific behavior. By doing this, we enable flexible interaction with different types of character, making our game more versatile as we introduce various enemy types. Now let's implement encapsulation in our character class by modifying how we manage the health attribute. In this version, the health variable is declared as private, which restricts direct access from outside the class. We then introduce a public property named health, which provides a controlled way to get and set the value of health. This property includes logic to ensure that when we attempt to assign a negative value to health, it instead defaults to 0. This encapsulation mechanism helps maintain the integrity of the character's state. Next, we'll adjust our Game Manager script to utilize this new encapsulated character class. Here, we instantiate a character object and assign it a name and an initial health value. As we proceed, we simulate damage taken by the character using the take damage method. Importantly, we also attempt to set the health to an invalid value of. However, thanks to our encapsulation logic, the health property will prevent the health from dropping below 0 and will instead reflect the safeguarded value. This example vividly showcases how well encapsulation safeguards our class's internal states against erroneous modifications. As we wrap up our discussion on master classes in C#, it's crucial to understand that while we have covered the fundamentals of creating and organizing classes, inheritance, polymorphism, and encapsulation, there's still much to explore. Consider looking into interfaces, which are similar to classes but define contracts that classes can implement. Not only does this help in maintaining code structure, but it also fosters easier integration and interaction between different parts of your game. To further expand your skills, practice creating various classes representing game entities such as weapons, items, or quests. Think about how they can interact using methods, properties, and encapsulation principles you've learned. By mastering classes and object-oriented programming techniques, you're well on your way to building complex and engaging games in Unity. Remember, the more you practice, the better your code organization will become. Keep coding and let your creativity flow as you embark on your game development journey. In today's lesson, we are diving into the essential techniques of asset management in Unity. We will explore the best practices for organizing and maintaining a streamlined workflow, which is crucial as your projects grow larger and more complex. So far, we learned the importance of mastering classes in C# for organizing code in Unity, focusing on the principles of encapsulation, inheritance, and polymorphism. We defined a basic character, class, and created instances of it, incorporating features like damage handling and class inheritance for specialized character types. We also emphasized encapsulation as a means of protecting the internal state of objects through controlled access. Lastly, we encouraged ongoing practice with class creation and interactions to enhance game development skills. Now we will cover asset management techniques essential for ensuring an organized and efficient development process. Asset management in Unity encompasses the strategies and practices involved in systematically organizing, accessing, and utilizing assets throughout the game development lifecycle. It is pivotal for maintaining a streamlined workflow and ensuring that your development process remains efficient, especially as projects scale up. A well-organized project enables developers to save time, reduce frustration, and enhance collaboration, which becomes increasingly important in larger teams or projects. Now let's take a look at how we can visually structure our assets in Unity for optimal organization. The hierarchical directory structure displayed in the code snippet illustrates a recommended organization method for assets within the Assets folder. Under the Models folder, we further categorize our assets into subfolders for characters, environments, and props. This division allows for easier navigation when managing numerous assets. Additionally, the Textures folder is organized into UI and characters, reflecting how essential it is to maintain clarity in your project structure. By adopting this hierarchy, you create a well-defined and coherent directory layout, simplifying asset retrieval during development. This kind of structured organization not only enhances workflow efficiency, but also improves team collaboration, particularly in larger projects with multiple contributors. As you build your game, you can continually refine and adjust this structure to suit your evolving asset needs, ensuring that everything is neatly categorized and easy to access. This practice ultimately leads to a more organized development process, allowing you to focus more on creativity and gameplay rather than searching for the right assets. Now let's take a look at how to implement consistent naming conventions for our assets. In our example, we have a structured list of asset names that follows a clear and systematic approach. By prefixing texture files with tex, sound files with snd, and using clear identifiers for scripts or characters, we create a naming system that improves organization and efficiency. For instance, we see texture files like TextGrass and TextSky, which immediately inform us of their type and purpose. Similarly, sound files such as SND Explosion and SND Jump signify their role in the game without requiring further clarification. This method allows developers to seamlessly identify and access assets based on their function, facilitating a smoother workflow. Next, we observe the naming convention's flexibility demonstrated by player-character script. This naming gives clear context that the script is specifically associated with the player character, preventing ambiguity. By adhering to this structured format, developers can minimize the time spent searching for files, leading to a more organized project as it scales up in complexity. Implementing such conventions is essential for maintaining clarity and efficiency in your development process. Now let's take a look at how we can optimize texture assets using Unity's built-in features. The code snippet demonstrates a straightforward method for loading a texture from your project's resources and applying compression to it, which is vital for performance. We start by utilizing the resources load method to get a TextureID object from a specified path. This approach allows us to access textures that are part of the game's resources folder. Next, we call the compress method on the loaded texture. Compression is crucial because it reduces the texture size in memory, minimizing the strain on the device's graphics capabilities. High-resolution textures can lead to longer load times and increased memory usage, especially on less powerful hardware, which is something we want to avoid for the best user experience. By applying compression to our textures, we balance the visual quality of our game with optimal performance, ensuring it runs smoothly across various devices. This practice is a key part of asset management, allowing us to maintain an efficient pipeline as our projects grow in scale and complexity. Remember that effective asset optimization can significantly enhance the overall gameplay experience. Now let's take a look at how we can implement asset loading using Unity's addressable asset system. In this script, we begin by defining a class called AssetLoader that inherits from MonoBehavior. This class contains a method named loadCharacter, which demonstrates how to load an asset asynchronously. In this example, we are specifically loading a game object identified by the address playerCharacter. When the loadCharacter method is called, it utilizes the addressable's API to initiate the loading process. The loadAssetAsync method is called, and it takes the address of the asset as a parameter. To handle the result of the loading operation, we subscribe to the completed event, which triggers the onAssetLoaded method once the asset loading is finished. Here, the script checks if the loading operation was successful. If it was, it instantiates the loaded game object, in this case, the player character. This approach not only optimizes loading times by fetching assets on demand, but also allows you to add any necessary setup for the character after instantiation, ensuring a smooth integration into your game environment. 5. Regular audits of your asset library *. Keeping your project lean is essential. Conduct regular audits of your asset library to prevent asset bloat, the unnecessary accumulation of unused or redundant assets. Tools like Unity's Asset Usage Detector can help identify assets that can be safely removed or archived. Regular assessments of your assets promote a clutter-free environment and ensure that only essential files are included in your project, optimizing performance and build size. Now let's implement a simple script that allows us to import assets into our Unity project programmatically. We begin by creating a class called AssetImporter, which inherits from MonoBehavior, allowing it to be attached to game objects within the Unity editor. Within this class, we define a public method named ImportNewAsset, which takes a string parameter file path. This parameter represents the file path of the asset we wish to import. By calling Asset Database import asset file path, we leverage Unity's Asset Database API to import the specified asset into our project. This method handles the import process under the hood, ensuring that the asset is configured correctly based on its file type, whether it's a texture, model, or any other supported asset. Utilizing this approach streamlines the workflow when managing assets, enabling developers to add resources to their projects quickly. By integrating this functionality into your development process, you can enhance productivity and maintain a well-organized project environment, further illustrating the benefits of effective asset management practices in Unity. In summary, effective asset management in Unity is anchored in organized structures, consistent naming, performance optimization, and regular audits. By adopting these techniques, you can enhance your workflow, improve team collaboration, and maintain a scalable project. Mastering these practices will ultimately empower you to bring your game visions to life more efficiently and with greater creativity. As we wrap up this lesson, remember that the way you manage your assets can make a world of difference in the development process. Keep practicing these asset management techniques, and you'll find that creating complex, engaging games becomes a much smoother journey. Next, we'll delve deeper into the manipulation of game objects, focusing on how to enhance the interactive elements of your games. Stay tuned for that exciting exploration. Embarking on the creation of your first scene in Unity is a pivotal moment in the game development process. It sets the stage for everything that follows, influencing how your game feels, how the player interacts with it, and ultimately how engaging the experience will be. So far, we learned the essentials of effective asset management in Unity, emphasizing the importance of a structured approach to organizing assets, including creating folders by asset types and establishing consistent naming conventions. We also discussed the optimization of asset usage for improved performance, the benefits of utilizing the addressable asset system for dynamic loading, and the necessity of regular audits to maintain a clean asset library. These practices will significantly enhance workflow efficiency and team collaboration throughout the development process. Next, we will explore scene preparation strategies to create interactive and immersive game environments. Now let's see how we can implement the foundational layout of our scene by creating distinct game objects for various zones. The code starts by defining a class called SceneSetup, which inherits from MonoBehavior, a fundamental Unity class that allows the script to be attached to game objects. Inside this class, the start method is invoked when the scene begins, making it the perfect place to initialize our environment. In this method, we create three game objects: Gameplay Area, Exploration Area, and Dialogue Area, each assigned a descriptive name that enhances organization within the hierarchy. By setting their transform position properties to specific coordinates, we establish distinct locations for these zones within the scene, each one serving a unique function. For instance, the gameplay area is positioned at the origin, while the exploration and dialogue areas are strategically placed along the x-axis. This approach not only provides clarity in our scene layout, but also sets the groundwork for the various interactions and gameplay mechanics we will implement as we further develop our game. Now let's see how we can instantiate multiple tree game objects in our scene using a prefab. In this code, we first declare a public variable named treePrefab, which allows us to assign the prefab for our tree in the Unity inspector. This practice ensures that we can easily change the tree design later on without modifying the script itself. Inside the start method, we use a for loop that runs 5 times. Each iteration of the loop generates a new tree at a specified position along the x-axis, spaced evenly apart by multiplying the loop index by 2. The instantiate method is called to create a new instance of treePrefab, placing it at a new vector 3 position while maintaining the default rotation via quaternion identity. This approach not only saves time by allowing us to create multiple trees with minimal code, but also ensures consistency in the design, as each tree is instantiated from the same prefab. As you implement this code, you'll notice how quickly and efficiently you can populate your scene while maintaining a cohesive visual style. Now let's implement a directional light in our scene to enhance its overall atmosphere. The code begins by creating a new game object specifically for the directional light, which is fundamental for simulating sunlight in your environment. We then add a light component to this game object, setting its type to directional, which casts light in a uniform direction across the scene, mimicking the sun's rays. To achieve the desired brightness, we adjust the light's intensity to 1F, making it bright enough to illuminate the surroundings effectively. Additionally, we set the light's color to white, ensuring a natural sunlight effect. One crucial step is to manipulate the light's rotation. By adjusting the angles, we can simulate the sun's position in the sky. In this example, we set the rotation using quaternion. Euler, giving the directional light a feeling of realism that can significantly affect the visual quality of the scene. Through this code, we not only improve visibility but also add depth and dimension with shadows and highlights, making the scene more immersive. Be sure to experiment further with the light's properties to find the perfect setup for your specific scene. Now let's see how we can implement material application to a game object in Unity. This script defines a class called MaterialSetup, which inherits from MonoBehavior, allowing it to be attached to a game object in the Unity editor. Within the class, there's a public variable named NewMaterial that you can assign in the inspector, giving you the flexibility to use any material you've created. In the start method, which Unity calls when the script is run, we create a primitive game object, a cube. The GameObject createPrimitive function is used here, which is a handy way to quickly generate basic shapes for testing and prototyping. Once the cube is created, we access its renderer component using getComponentRenderer. This line is crucial as it allows us to manipulate the visual properties of the cube. Finally, we assign the previously defined new material to the cube's material property. This effectively applies your custom material, transforming the appearance of the game object to match your scene's aesthetic. It's an excellent starting point for creating visually rich environments in your game. Now let's see how we can implement a collectible item that players can interact with in our game. In the provided code, we define a class named Collectible, which inherits from MonoBehavior, enabling it to be attached to a game object in Unity. Inside this class, we use the onTriggerEnter method, which is a built-in Unity function that gets called when another collider enters the trigger collider attached to the collectible object. This method takes a parameter called Other, which represents the other collider involved in the trigger event. We begin by checking if the other collider has the tag player, using the compareTag method for efficiency. If the player collides with the collectible, it proceeds to execute the logic inside the conditional statement. Here, you may want to add points or any interaction logic pertinent to your game. For feedback, we log a message indicating that the item has been collected, enhancing the player's experience. Finally, we use destroyGameObject to remove the collectible object from the scene after the player collects it, ensuring it doesn't clutter the environment. This straightforward script forms the basis for interactive gameplay mechanics, allowing players to engage with elements in your game world. Now let's see how we can implement a camera follow script that enhances our scene's perspective. This script allows a camera to dynamically follow the player, ensuring they remain centered in the frame, which is crucial during exploration or action sequences. In this script, we start by referencing the player's transform, which allows the camera to track its position. We use the lateUpdate method, which is called after all other updates, ensuring that the camera's position is adjusted after the player's movement. This avoids any potential jittering, providing a smooth viewing experience. Next, we calculate a new position for the camera, positioning it slightly above and behind the player. By setting the camera's position to this new vector, it creates a natural following effect. Additionally, we use the lookat method to ensure that no matter where the player moves, the camera is always oriented toward them, keeping the action in view. This attention to camera angles and perspective can significantly enrich the player's immersion, making the gameplay feel more engaging and cinematic. Now let's implement the following code to optimize our scene for performance using occlusion culling. In this snippet, we create a new class called OcclusionSetup, which inherits from Unity's MonoBehavior. Inside the start method, we enable occlusion culling by setting the useOcclusionCulling property of the main camera to true. This simple line of code instructs Unity to not render objects that fall outside the camera's view, effectively reducing the number of draw calls and improving overall performance, especially in complex scenes filled with multiple assets. Utilizing occlusion culling is essential for maintaining a smooth gameplay experience, as it minimizes the load on the rendering engine by disregarding unnecessary objects. As you work on larger scenes, incorporating this feature will help ensure that players enjoy visually stunning environments without the frustration of lag or stutter. Regularly monitoring your performance metrics in Unity will allow you to make necessary adjustments, further enhancing gameplay fluidity and responsiveness. As we wrap up our exploration of scene preparation strategies, remember that the process of crafting a scene is both creative and technical. From envisioning the scene's purpose and layout to implementing lighting, textures, and game mechanics, each step is critical in creating an engaging player experience. With every asset you place, every script you write, and every light you adjust, you're bringing your game world closer to life. In your journey of game development, scene preparation will become second nature. As you continue crafting, remember to experiment and take risks. Some of the best innovations come from trying something different, so don't be afraid to think outside the box. In the following lessons, we will delve deeper into manipulating game objects, enriching the interactivity in your game. Exciting times lie ahead. Let's keep building. C# is a modern, object-oriented, and type-safe programming language developed by Microsoft. Today, we're diving into the basics of C# syntax. Whether you're a beginner or looking to brush up on your skills, understanding the syntax is crucial for writing efficient and effective code. Next, we will write a simple C# program that illustrates the basic structure of the language, which includes defining a class and a main method. In this example, we begin by importing the system namespace, which is a collection of fundamental classes essential for C# programming. The class program declaration defines a new class named program, serving as a blueprint for our application. Within this class, we have the main method, which acts as the entry point for our program. This is where the execution begins, and any executable code must be placed within this method. Here we've implemented a simple output statement using console, WriteLine, which prints hello world to the console. This showcases how we can display information to users, a fundamental aspect of many applications. It's important to note that every statement in C# ends with a semicolon, indicating the conclusion of that command. By understanding this basic structure, you'll have a firm foundation to expand upon as we explore more complex programming concepts in C. Now let's implement the following code to declare and initialize some basic variables that we will use throughout our program. In C, we start by declaring variables with specific data types to store different kinds of information. For instance, we create an int variable named a and assign it the value of 25, which signifies the age of a person. Next, we have a float variable called height initialized to 5.9f, noting the f suffix indicating it's a floating point number, essential for representing decimal values. Then we declare a bool variable named isStudent, assign the value true, which can be used to represent a simple binary state. Lastly, we introduce a string variable called name, set to Alice, for storing a sequence of characters. Each of these variables is crucial for holding relevant data that can be manipulated or displayed later. By defining these variables clearly, we maximize code readability and maintainability, setting a strong foundation for any future operations or calculations we may want to perform. Next, let's implement some arithmetic operations using C#. Arithmetic operators are fundamental as they enable us to perform various mathematical calculations. For instance, when we declare an integer variable called sum and set it to the result of adding 5 and 3, we are effectively demonstrating how to calculate and store the outcome of a simple addition operation, which gives us a value of 8. Similarly, by creating another variable, product, and assigning it the result of multiplying 5 by 3, we illustrate how to execute a multiplication operation, producing a value of 15. These operations exemplify how C# allows us to handle numerical values succinctly and effectively. Now let's explore how we can use relational operators to compare values. By declaring a Boolean variable named isGreater, we can check if 5 is indeed greater than 3, which results in a true value. Additionally, we can create another Boolean variable, isEqual, to verify if both values are equal. This comparison returns true since both are indeed 5. Lastly, let's see how we can implement logical operators to combine Boolean expressions. For instance, by initializing a Boolean variable condition with a logical AND operation, we can evaluate whether both conditions, 5 is greater than 3 and 3 is greater than 1, are true, yielding another true result. Understanding these operators empowers you to write more complex and effective logic in your C# programs. Now let's take a look at control flow statements, which allow our programs to make decisions based on certain conditions. The first example demonstrates how to use the if statement to check if a user is a student. If the condition evaluates to true, the program welcomes the user to the student portal, otherwise, it directs them to the public portal. This branching logic enables us to create distinct paths for different scenarios, making our applications more interactive and user-friendly. Next, we will implement an if statement in conjunction with an else-if clause, which allows us to evaluate multiple conditions. In this code, we check the user's age and categorize them as a minor, an adult, or a senior citizen based on their age range. The use of logical operators like and gives us the flexibility to create more refined conditions, enhancing our decision-making process. This structure is vital for tailoring user experiences and can influence game dynamics significantly, guiding the narrative according to user input. Understanding these control flow constructs is essential as we deep dive into programming for interactive applications. Now let's see how we can implement a for loop in C#. A for loop is particularly useful when you know in advance the number of iterations you would like to perform. In the example, we initialize a variable I to 0 and specify the condition that I must be less than 5 for the loop to continue executing. Each time through the loop, we print the current value of I to the console. This setup allows us to efficiently execute the loop 5 times, clearly demonstrating the power and simplicity of the for loop structure. It's crucial that we increment I with each iteration using I++, ensuring that the loop will eventually terminate once the condition is no longer met. Next, we'll look into a while loop, which serves a different purpose. In this scenario, we start with a count variable initialized to 0. The loop checks whether count is less than 5. While this condition remains true, the loop will execute. Each time through the while loop, we print the current count and then increment count by 1 to avoid creating an infinite loop. This example highlights the flexibility of while loops for situations where the number of iterations isn't predetermined, allowing the loop to run based on dynamic conditions. Now let's take a look at collections, specifically arrays and lists, which are fundamental in managing groups of data in C. First, we define an array named numbers that holds 5 integers. Notice the fixed size of the array, meaning that once defined, it cannot change its length. Accessing elements within this array is simple. For example, the first element can be retrieved using the index 0, which outputs 1. Next, we will implement a list to show the flexibility of dynamic collections. By using the list_t class, we create a list that can grow and shrink as needed, perfect for situations where the number of items is not known in advance. In our example, we initialize a list of strings called names. With the add method, we can easily add names like Alice and Bob into the list. Additionally, accessing elements in a list is as straightforward as in an array, allowing us to print the name at index 1, which returns Bob. Using lists not only simplifies managing dynamic data, but also provides various methods to manipulate that data more effectively compared to arrays. Now let's take a look at how we can create and utilize methods to enhance our code organization and reusability. Here, we define a simple method named greetUser that takes a string parameter called username. This method utilizes the console WriteLine function to output a greeting message that incorporates the provided username. The key part to note is the use of string interpolation, which allows us to dynamically insert the username variable into our greeting string for a personalized touch. To call this method, you simply invoke it from the main method and pass a specific name as an argument, such as Alice. This execution results in a greeting displayed on the console. Hello, Alice! Utilizing methods like this not only structures your code more effectively, but also promotes clarity by encapsulating specific tasks. As you gain familiarity, you'll discover how parameters can expand functionality and return types can add further flexibility to your methods, creating even more robust applications. Now let's take a look at how we can define a simple class in C. In object-oriented programming, classes serve as blueprints for creating objects, allowing us to encapsulate data and behavior together. Here we define a class with 2 properties, make and model, both of which are strings that represent the car's manufacturer and its model name. These properties are created with the use of C#'s automatic property syntax, enabling easy get and set functionality. Next, we implement a method called drive, which enhances the class's functionality. This method outputs a message indicating that the car is driving, integrating the make and model properties into a formatted string. After defining the class, we proceed to demonstrate its usage by instantiating an object of the car class named myCar. We set the properties of myCar to Toyota for make and Corolla for model. Finally, we invoke the drive method to illustrate how the object behaves when we call its method, effectively showing the power of encapsulation and method invocation in action. Now let's implement exception handling to manage potential runtime errors in our program. The code begins with a try block where we attempt to divide a number by 0. This operation is invalid and will throw a divide by 0 exception. Instead of allowing the application to crash, we use a catch block that specifically handles this exception. When the exception is detected, the code within the catch block executes, providing a user-friendly message that indicates the error. This approach allows our application to fail gracefully, enhancing the user experience. Furthermore, we have a finally block that executes regardless of whether an exception was caught or not. This is particularly useful for executing cleanup code or ensuring that certain actions like logging or releasing resources are always performed. By incorporating these elements try, catch, and finally we create a robust error handling mechanism, safeguarding our application from unexpected crashes and improving its reliability. Understanding and implementing exception handling is crucial as we refine our scripting techniques in C. Now that we've explored the syntax basics of C#, let's summarize what we've covered so far. We've looked at the structure of a C# program, variables and data types, operators, control flow statements, loops, collections, functions, classes, and exception handling. This foundational knowledge of C# syntax is essential as we build more complex scripts and applications, particularly in Unity. In our next lessons, we'll explore how to apply this syntax within Unity, integrating it to manipulate game objects and create dynamic interactions that make our gameplay exciting and fun. By mastering C# syntax, you're not just learning a programming language, you're opening doors to developing intricate games and applications that can engage users deeply and effectively. So buckle up and stay tuned because there's so much more to learn and create in the world of C. Control structures are the cornerstone of C# programming, directing the flow of execution and enabling dynamic responses within applications. Understanding these control structures is essential because they allow you to dictate how and when specific parts of your code should run based on conditions or repetitions. So far, we have covered the basics of C# programming, including its structure, variables, data types, operators, control flow statements, loops, collections, functions, classes, and exception handling. Each of these elements plays a crucial role in building effective and efficient code. We also established the significance of mastering these concepts as a foundation for developing applications, particularly in the context of Unity. In this lesson, we will talk about control structures, specifically how they manage the flow of our code, including decision-making, looping through data, and more. Now let's take a look at a practical example of how decision-making works in C#. In this code, we begin by declaring and initializing an integer variable called score, which represents a player's score in a game. We then use an if statement to check if the score is 90 or higher. If this condition is true, the program executes the code within the if block, displaying a message that the player has performed excellently. If the score is not high enough to meet this first condition, the code moves on to an else if statement that checks if the score is at least 80. If the score meets this criterion, a message indicating great work is displayed. Lastly, if neither of those conditions is true, the else block executes, providing encouragement to the player to keep trying. This structured approach allows us to determine which feedback the player receives based on their performance, illustrating the power of control flow in programming and how we can create dynamic responses in our applications. Next, we will write a switch statement to effectively manage multiple character selections in our game. In this code, we start by declaring a string variable named characterType, initializing it with the value warrior. The switch statement then examines this variable to determine which character has been selected. It includes several cases. If the character type is warrior, it prints a message highlighting the strength and bravery of this character. Similarly, if the selection is mage, it acknowledges the character as a master of spells, and if it's rogue, it emphasizes stealth and cunning. Each case concludes with a break statement, which is essential for preventing the flow from falling through to the next case. This structure not only makes the code easy to read, but also allows for efficient management of the character selection process. Finally, if none of the defined cases match the character type, the default case executes, providing a message for any unrecognized input. This additional safeguard enhances user experience by ensuring that the game handles unexpected selections gracefully. Now let's see how we can implement a for loop to display a sequence of numbers. In this example, we define a loop that initializes a variable I to 1 which serves as our starting point. The loop is set to continue executing as long as I is less than or equal to 5, ensuring that we display the numbers from 1 through 5. After each iteration, we increment I by 1 using the I++ statement, which allows the loop to progress. Inside the loop, we utilize console writeLine to print out the current value of I, prefixed with number. This gradual counting approach demonstrates the fundamental behavior of iteration in programming, making it straightforward to understand how loops operate. The for loop is particularly effective here since we know exactly how many times we want to iterate, making it ideal for situations where the range is predetermined. By understanding this structure, you will find numerous applications for loops in your coding projects, allowing for efficient execution of repetitive tasks. Next, we will implement a countdown using the while loop, an excellent choice for scenarios where the number of iterations isn't predetermined. In our example, we initialize a countdown variable set to 5, representing the starting point of our countdown. The while loop checks the condition that the countdown value must be greater than 0 for its body to execute. Inside the loop, we print the current value of the countdown, giving real-time feedback to the user. After printing, we decrement the countdown variable using the decrement operator. This action decreases the countdown by 1 with each iteration, gradually bringing it closer to 0. The loop continues to execute as long as the countdown variable remains positive. Once it hits 0, the loop ceases to run, and we then proceed to print blast off, which signifies the end of the countdown. This implementation neatly demonstrates how a while loop can manage repetitive actions based on a condition, making it ideal for countdown scenarios where the iteration count is dictated by the changing state of a variable. Now let's see how we can implement a do while loop, which is a useful control structure that guarantees the loop body executes at least once before evaluating the condition. In our example, we begin by initializing an attempt variable to 0, which will keep track of the number of connection attempts. The loop is structured so that it attempts to connect, displaying a message to indicate the action taken. Regardless of the value of attempt, the code inside the do block runs immediately, ensuring that at least one connection attempt is made. After the attempt is made, the attempt variable is incremented. The loop continues to execute until the condition specified in the while clause evaluates to false. In this case, it continues as long as the attempt is less than 3. Once 3 attempts have been made, the loop stops and a completion message is printed. This structure is particularly useful in scenarios where you want to ensure that a specific action occurs at least once, even if the condition for repeated execution isn't met from the start. It effectively allows for controlled repetition based on user-defined criteria. Now let's see how we can implement control statements like break and continue in a for loop, which allow us to manage loop execution based on specific conditions. In our first example, we set up a loop that iterates from 1 to 10. Within the loop, we include a condition that checks if the loop variable I equals 5. When this condition is met, we print a message indicating that we are breaking out of the loop and utilize the break statement to exit the loop entirely. This illustrates how break provides a powerful way to control the flow of execution, allowing us to stop processing as soon as we reach a certain point. Next, we will write the following example where we use the continue statement to refine our loop's behavior. Again, iterating from 1 to 10, we check if the current number is even. If it is, we employ continue to skip the rest of the current iteration, effectively bypassing the print statement for even numbers. As a result, only odd numbers are displayed. This feature of continue enables us to manage data more efficiently, focusing solely on the elements of interest while ignoring others based on defined conditions. Now let's implement a function that evaluates a list of scores, determining if each score is passing or failing. This function, named evaluateScores, uses a for-each loop to iterate through an array of integers representing the scores. For each score in the array, the code checks whether it meets the passing criterion of being greater than or equal to 60. If a score meets the passing threshold, the function prints a message indicating a pass. Otherwise, it outputs fail. This approach demonstrates how control structures can be effectively combined within functions to introduce dynamic decision-making based on the scores provided. Utilizing a for-each loop here simplifies the process of iterating through the scores, making the code cleaner and easier to understand compared to traditional for loops. Additionally, by embedding conditional logic with the if statement, the function is able to provide immediate feedback on each score's status, showcasing how control structures enhance the adaptability and responsiveness of our functions in C#. This lays the groundwork for developing more complex applications that require real-time data evaluation and user interaction. As we come to the close of our discussion about control structures, it's important to reinforce their significance in programming. They enable interaction with data and user choices, allowing applications to evolve based on dynamic situations and inputs. Mastery of control structures is not only a fundamental aspect of C# programming, but also a stepping stone toward creating engaging and interactive applications, particularly in game development environments like Unity. Now that you have a solid understanding of how control structures work in C#, you're ready to implement this knowledge into your own programming projects, especially as we advance into topics surrounding game objects and interactive gameplay mechanics. These tools will facilitate rich interactions and immersive experiences for users, positioning you on a path toward developing captivating applications. So, remember that control structures are your best friends in coding. They guide the flow of your applications and build the logic that drives user engagement. Until our next session, keep experimenting with what you've learned today and happy coding. The Unity script lifecycle is a meticulously designed framework that ensures scripts react appropriately at various stages of a game's runtime, from initialization to the final cleanup. Today, we are diving deep into this lifecycle, exploring its nuances and functionalities. So far, we covered control structures in C#, which dictate the flow of code execution through decision-making and looping constructs. Now, we will talk about the Unity script lifecycle, from initializing game objects to efficiently cleaning up as the game progresses. Let's unravel this intricate web of methods and events vital for managing behaviors in Unity. To understand the Unity script lifecycle, we can break it into three primary phases: initialization, the game loop, and cleanup. Each phase consists of specific methods that Unity calls at predetermined moments during the game's execution. Now let's take a look at the implementation of the game initializeClass, which demonstrates the **awake method in Unity's initialization phase. The game initializeClass inherits from mono behavior, enabling it to utilize Unity's lifecycle methods. Within this class, we declare a private integer variable named playerScore, which will hold the player's score. Next, we define the **awake method. This method is a crucial part of script execution, as it runs when the script instance is being loaded, even before gameplay starts. In our implementation, we initialize the playerScore to 0. This ensures that the game begins with a clear starting point for the score. Following the initialization, the code logs a message to the console, confirming that the awake method has been called and displaying the initialized score. This logging is essential for debugging purposes, allowing developers to verify that initializations are occurring as intended. By setting up the player's score in awake, we ensure that it's ready for any gameplay mechanics that will follow, establishing a solid foundation for the game's scoring system. Next, we will write the following implementation of the onEnable method within our player class. This method plays a crucial role in the Unity lifecycle, as it is triggered every time the player game object is activated. Here, we initialize the player's health, setting it to a predetermined value of 100 each time the object is enabled. This ensures that every time the player comes back into the scene, they start with a full health bar, promoting fairness in gameplay. Furthermore, to provide feedback during development, we include a debug log statement that outputs a message to the console every time onEnable is called. This message confirms that the method has executed properly and displays the current health value. This practice not only helps in debugging, but also in understanding how the game object's state is managed throughout its life cycle. Thus, utilizing onEnable strategically allows for dynamic control over our player's state, enhancing the overall game experience by resetting vital attributes when needed. Now let's implement the following code to see how our game manager can effectively manage the player's state during the game. In this script, we create a game manager class that derives from MonoBehavior. The game manager contains a public reference to a player object, allowing it to interact with the player's properties directly. As the game starts, the start method is invoked after all awake calls have been completed, ensuring that the player's health and related initializations are fully set up. Within the start method, we utilize debug log to display a message indicating that the start method has been called alongside the player's initial health. This is crucial because it confirms that the player's awake method has executed prior, allowing us to depend on the player's state being ready for any game logic we want to implement. This dependency on the start method ensures that we can link components in a coherent fashion, establishing interdependencies in game objects, essential for creating a fluid gameplay experience. By managing these interactions correctly, we lay a strong foundation for the game's mechanics and player experience. Now let's see how we can implement player movement in Unity using the update method. This method is called once per frame, making it ideal for capturing real-time user input and updating the player's position accordingly. In our player movement script, we define a public variable for speed, allowing easy adjustments within the Unity editor. Inside the update method, we gather input from the player using the input getAxis function, which captures key presses for horizontal and vertical movement. This input is then multiplied by the speed variable and time delta time. By incorporating time delta time, we ensure that the movement remains smooth and consistent across different frame rates, allowing for a seamless gameplay experience. The calculated movement values, move horizontal and move vertical, are then passed to the transform translate method. This method applies the changes to the player's position in the game world. As a result, every time the update method runs, our player character can respond instantly to input, creating a responsive and fluid movement system crucial for any effective game design. This approach exemplifies how Unity's game loop facilitates real-time interactions within the gameplay framework. Next, we will write the following code to demonstrate how to apply forces using Unity's physics system. In this script, we create a class named *PhysicsHandler that interacts with a rigid body component, which is essential for handling physics simulation in Unity. First, within the *awake* method, we retrieve the rigid body component attached to the game object. This initialization is crucial because it sets up our object for physics interactions that will occur later. Now let's implement the *fixedUpdate method, which is specifically designed for physics-related updates. In this method, we apply an upward force to the rigid body every fixed frame. The force vector is defined as *vector 3 up *5f, ensuring that the object continuously moves upward at a consistent rate. Utilizing fixed update for this type of operation guarantees that our physics calculations remain stable and predictable, which is essential when simulating real-world behavior in games. By executing the FOSS application here, we ensure that the movement adheres to Unity's physics calculations, allowing for a smooth and accurate interaction with other physics-based elements in the game environment. Now let's take a look at how to implement a smooth camera follow mechanism behind the player character. In our example, we define a class called cameraFollow, which inherits from MonoBehavior, allowing it to function as a script attached to a game object in Unity. We first declare a public transform variable named player, which references the player's position in the game world. This public access modifier allows us to easily assign the player game object through the Unity inspector, connecting our camera to the player seamlessly. The key functionality resides within the lateUpdate method, which is invoked after all update methods have been executed for the current frame. This timing ensures that any character movement occurs before the camera adjusts its position, preventing any visual lag. Inside the lateUpdate method, we update the camera's position based on the player's coordinates. By establishing a new vector 3 for the camera's position, we offset the camera slightly above and behind the player, ensuring a clear view of the character and the gameplay environment. This method effectively creates a dynamic and responsive camera that enhances the player's experience, closely tracking movements and allowing for a smoother gameplay experience. In the cleanup phase, we will now implement a method to handle deactivation events of our game objects. Let's take a look at the onDisable method implemented in the enemy class. This method is automatically triggered when the game object is deactivated in Unity, making it an ideal place to manage any ongoing processes related to the object. Within onDisable, we have a log message indicating that the enemy has been deactivated. This is useful for debugging, allowing developers to track when enemies are no longer active in the game. Additionally, it's critical to pause or stop any ongoing activities such as coroutines or event subscriptions. By stopping these processes, we ensure that the deactivated game object does not continue to consume resources or respond to events, which could lead to unexpected behaviors or performance issues. Overall, utilizing onDisable effectively enhances memory usage and performance in your Unity projects, ensuring a stable and smooth gameplay experience. This method encapsulates an essential aspect of resource management in the Unity script lifecycle. Next, we will implement the following code for the cleanup phase in Unity, specifically focusing on the onDestroy method. This method is crucial as it is called just before a game object is permanently destroyed, allowing developers to execute necessary final actions such as saving data or releasing resources. In our example, we have a score manager class, serving as a dedicated handler for player scores within the game. Within the onDestroy method, we utilize debug log to indicate that the method has been called, which is useful for monitoring the flow of operations during development. This serves as output in the console, informing the developer that the score saving process is taking place. It's imperative to incorporate logic that captures the player's final score before the game object and its associated data are cleared from memory. By utilizing onDestroy for saving critical information, we ensure that players do not lose their progress, maintaining a seamless and rewarding gaming experience even when the object is removed or the game terminates. This exemplifies the importance of managing data integrity and resources in the Unity lifecycle, ensuring that our game operates smoothly and effectively. Summing up, understanding Unity's script lifecycle is paramount for crafting well-structured and efficient scripts. By applying methods like awake, onEnable, start, update, fixedUpdate, lateUpdate, onDisable, and onDestroy, developers can optimize game behavior, ensure resources are managed wisely, and maintain smooth gameplay dynamics. With this knowledge, you'll find that Unity can facilitate intricate behaviors for game objects, making your games not only playable but also enjoyable. Keep experimenting with these concepts as you embark on your journey through Unity game development. The mastery of script lifecycles will enhance your skills in creating immersive and interactive experiences. Now let's explore the player script, which establishes the foundational behavior for our player character. In this script, we've defined a public integer variable named health that initializes at 100, representing the player's starting health. The take damage method is essential for modifying this health value. It accepts an integer parameter, damage amount, which is subtracted from the player's current health whenever the method is called. Additionally, a debug log statement provides real-time feedback in the console, tracking the player's health after taking damage. Now let's examine the UI Manager script, which is responsible for updating the user interface with the player's health. This script contains a public reference to the player instance, allowing UI Manager to access the player's public health variable directly. Within its update method, the script continuously refreshes the text of a UI element to display the current health, making the player's status always visible to the user. This straightforward approach demonstrates how easily data can be shared between scripts in Unity, enabling dynamic UI updates in response to game events such as health changes. Now let's implement an event-driven approach to enhance our player script. In this updated version, we define a delegate named onPlayerDamage, which allows us to create an event, playerDamaged, that can be triggered whenever the player takes damage. This allows different components in the game to respond to this event without needing direct references to one another, which promotes a decoupled architecture. Within the take damage method, whenever the player sustains damage, we reduce the health and invoke the playerDamaged event, passing the current health to any listeners that have subscribed to the event. Next, we will write the UI Manager script to respond to this event. In the start method, we subscribe to the playerDamaged event from the player script, linking it to our update health UI method. This means that every time the player takes damage, the update health UI method will be automatically called, allowing for real-time updates to the user interface. This approach makes the code cleaner and more maintainable, as each component can independently react to events without tightly coupling their functionality. Now let's take a look at how we can modify our player script to incorporate a healing mechanism. In this updated version of the player class, we've added a public method named heal, which takes an integer parameter representing the amount of health to restore. This method increases the player's current health variable and logs a message to indicate the new health status. Next, we will implement a game manager script designed to interact with the player script. This game manager will monitor player input continuously in the update method, specifically checking for when the H key is pressed. Upon detecting this input, the game manager will call the heal method on the player instance, restoring a predefined amount of health. This approach exemplifies a straightforward communication technique between scripts, utilizing direct function calls to facilitate interactions. By ensuring that the player instance is properly assigned in the game manager, we can avoid null reference errors, leading to a more robust and crash-free game. Thus, through this integration, we establish an effective way to enhance player experience by allowing health restoration during gameplay. Now let's implement a messaging system using the Message Manager class, which will facilitate communication between scripts without tight coupling. This class is designed as a singleton, ensuring only one instance exists throughout the game, which simplifies message handling. In the awake method, we check if the instance is null. If it is, we assign this instance and prevent it from being destroyed on loading new scenes. Moving forward, the subscribe method allows other scripts to register their interest in specific messages by adding their listener methods to a dictionary entry keyed by the message string. If the message doesn't exist, it initializes it to null, ensuring that we can append listener actions without overwriting previous ones. Conversely, the unsubscribe method permits scripts to deregister their listeners, providing flexibility in managing how different parts of your game respond to events. Finally, the sendMessage method enables any script to broadcast a message, which will invoke all registered listeners for that particular message, passing along any optional parameters. This design promotes a highly decoupled architecture, making it easier to maintain and scale your project. It's essential to keep performance in mind while employing different communication techniques. Public variables and direct method calls offer speed and simplicity for straightforward interactions, while events and message systems provide more flexibility at greater complexity and potential performance costs. Therefore, selecting an appropriate communication method depends on your unique use case and project size. In summary, inter-script communication in Unity can be achieved in various ways, from using public variables and properties to more sophisticated approaches like events, direct method calls, and message systems. Understanding and implementing these techniques will undoubtedly improve your game's architecture, enabling you to create more dynamic and interactive experiences. You've come a long way in mastering script communication, and with practice, you'll be crafting engaging gameplay that keeps players coming back for more. Until next time, happy coding. Exploring Unity's API unveils a robust system crucial to game development. In this lesson, we will delve into the exciting world of the Unity API and the component system, learning how to leverage these tools to enhance our game development experience. So far, we learned about the importance of inter-script communication for dynamic gameplay in Unity and the various techniques that facilitate this communication. We explored methods such as public variables, events with delegates, and public methods for script interactions. Additionally, the messaging system was introduced as a more decoupled approach for communication between scripts. Understanding these techniques enhances your game's architecture and interactivity. Now we will talk about the Unity API and how to effectively use the component system to build interactive and engaging game elements. Now let's see how we can create and manipulate a simple cube in Unity. In this script, we utilize the GameObject class from the Unity API to instantiate a primitive cube in our game. The start method is a special function that is called once when the script is initialized, allowing us to set up our game objects promptly. Within this method, we invoke GameObject, create primitive type cube, which generates a cube and assigns it to a variable named cube. To position our cube effectively in the 3D space, we modify its transform position property to 0, 0, 0, placing it at the center of the scene. Additionally, we utilize the transform local scale property to set its size, here defining the cube's scale to 1, 1, 1, which is its default size. This snippet demonstrates the simplicity of using the Unity API for object creation and manipulation, laying the groundwork for more complex behaviors and interactions as you delve deeper into game development. Now let's see how we can add physics to our cube by attaching a rigidbody component. After creating the cube object with the GameObject, create primitive method, we position it in the scene at coordinates 0, 1, 0. This sets it above the ground, ensuring that it will fall due to gravity when we attach the rigidbody. By invoking add component rigidbody, we enhance the cube with physics properties, enabling it to respond to forces and collisions in the game world. Without this component, the cube would remain static, lacking any interaction with the environment. The rigidbody allows the cube to experience gravity, be affected by other physics interactions, and enables us to manipulate its behavior in a physically realistic manner. This illustrates the powerful component system in Unity, where we can easily compose our game objects with specific functionalities to create a dynamic and engaging gameplay experience. By understanding how to integrate components like rigidbody, we pave the way for rich interactions within our game scenarios. Now let's take a look at how we can continuously rotate a cube in our Unity scene. In our rotateCube class, the start method is executed when the script first runs, and here we create a cube using Unity's GameObject, create primitive method, positioning it at 0, 1, 0 above the ground. We also attach a rigidbody component to allow the cube to interact with Unity's physics system, enabling it to respond to forces like gravity. Next, in the update method, which is called once per frame, we implement the logic for rotating the cube. Specifically, we utilize the transform rotate function to apply a rotation around the y-axis. The rotation speed is set to 20 degrees per second, but it's multiplied by time delta time to ensure that this speed remains consistent regardless of the frame rate. This approach allows for smooth and uniform rotation of the cube, enhancing the overall visual appeal of our game. By understanding and implementing the mono behavior and its life cycle methods, we can effectively create dynamic behaviors in our game objects. Next, we will implement collision detection in our project using Unity's built-in physics functionality. We start by creating a cube in the scene with the GameObject, create primitive method, which simplifies the process of generating a basic cube shape. To allow this cube to physically interact with other objects in the game, we add a box collider, which defines its physical boundaries, and a rigidbody, enabling it to respond to physical forces like gravity and collisions. The core of our collision detection mechanism resides in the onCollisionEnter method, which is a built-in Unity callback. This method automatically gets called whenever our cube collides with another collider. Inside this method, we use collision GameObject, compare tag, player, to check if the colliding object has the tag player. This approach is efficient for identifying specific game objects without hard-coding their names into the logic, promoting cleaner code maintenance. If the condition is met, we log a message to the console, indicating that the cube has successfully collided with the player character. This setup is fundamental for creating responsive and interactive game mechanics in Unity. Now let's see how we can implement character movement using Unity's input system with our cube. In this code, we create a simple script that allows us to control the movement of a cube object using the arrow keys on the keyboard. The script first creates a cube and adds a rigid body component to it, which enables physics interactions for the object. We set the initial position of the cube in the game scene, allowing it to start at a specified location. As the game runs, the update method is called every frame. Here we capture user input for horizontal and vertical movements by using the input getAxis method. This method reads the key presses for the arrow keys and translates them into a smooth movement vector. We then multiply this vector by a predefined movement speed and the time delta time to ensure consistent movement regardless of the frame rate. Finally, we employ the transform translate method to move the cube in the game world according to the user's input, enabling an interactive experience where players can actively control the cube's position within the scene. Next, we will implement a coroutine to create a fading effect for our cube. The fadeCube class starts by defining a private renderer variable to access the cube's material properties and a color variable to hold the target color. Within the start method, we create a cube as before and retrieve its renderer component, allowing us to manipulate its color. Now let's take a look at how we manage the fading in the fadeOut coroutine. This method gradually decreases the alpha value of the cube's color from fully opaque to fully transparent. The coroutine iterates through a loop, decreasing the alpha value in increments of 0.1 and updates the cube's material color accordingly. Importantly, we use yield_return_new_wait for seconds 0.1f to pause the execution of the coroutine for a brief moment during each iteration. This delay allows Unity to render the color changes smoothly without freezing the game's main thread. By using coroutines in this manner, we effectively enhance our game's visual feedback, making it more engaging for players as the cube fades in and out seamlessly. Now let's take a look at how we can utilize Unity events to create a loosely coupled architecture in our scripts. In the provided example, we declare a public Unity event named onPlayerCollide to facilitate event-driven communication between different objects. During the start method, we check if the event is null and instantiate it if necessary. By subscribing the handlePlayerCollision method to the onPlayerCollide event, we ensure that our specified method will respond when the event is invoked. When a collision occurs, specifically with a game object tagged as player, we invoke the onPlayerCollide event. This invocation triggers all methods that are subscribed to the event, meaning our handlePlayerCollision method will execute and log a message to the console. This setup allows diverse game objects to react to player collisions without needing to know the details of each other's implementations. By leveraging Unity events, we enhance the modularity and scalability of our components, paving the way for more maintainable and organized code as our project grows. Finally, to wrap it all up, it's important to remember that the Unity API and component system not only provide the tools needed for creating engaging gameplay, but also allow developers to maintain a clean and manageable codebase. As you continue learning and building with Unity, keep experimenting with different components and explore the vast capabilities offered by the API. By integrating these systems effectively, you will be well on your way to creating immersive and interactive experiences in your games. In conclusion, we have explored the foundational aspects of the Unity API and the component system. We learned about creating game objects, adding components, utilizing physics, handling user input, managing events, and implementing coroutines for smooth gameplay. These concepts are vital to mastering Unity and game development as a whole. As you advance, continue to build upon the knowledge you've gained here, and you will develop the skills needed to create amazing games. Happy coding! Now let's see how we can implement asset loading using Unity's asset bundles efficiently. We begin by creating a class called LevelLoader, which inherits from MonoBehavior, allowing us to attach it to a game object in our scene. Inside this class, we declare a public string variable bundle URL that will hold the path to our asset bundle. When the game starts, the start method triggers a coroutine, loadLevel, to handle the asynchronous loading process. In the loadLevel coroutine, we attempt to load the asset bundle using the specified URL. It's important to check if the bundle was successfully loaded. If not, we log an error. If the bundle is valid, we proceed to load a game object named LevelPrefab from the asset bundle and instantiate it in the scene. This approach allows the game to only hold necessary assets in memory, enhancing performance. Finally, once the asset level has been instantiated, we call unload on the bundle to free up resources, ensuring that our game remains lightweight and efficient. This technique is vital for managing memory effectively, especially in larger games with multiple levels. Now let's see how we can implement a simple object pool in Unity to optimize game performance. The Object Pool class maintains a queue of inactive game objects, which allows for efficient reuse rather than frequent instantiation and destruction. In this class, we define a public variable for the prefab that we want to pool. This makes it easy to assign the game object type we wish to manage via the Unity inspector. The core functionality is encapsulated in two methods, getObject and returnObject. When requesting an object with getObject, the pool checks if there are any available objects in the queue. If an object is available, it is dequeued and activated for use, ensuring seamless gameplay. If no objects are available, the method instantiates a new prefab. Conversely, when a game object is no longer needed, the returnObject method is called. This method deactivates the object and enqueues it back into the pool, ready for future reuse. By employing this pattern, your game can significantly reduce memory allocation and performance overhead, especially in action-packed scenarios where game objects are frequently created and destroyed. Now let's see how we can implement caching references in Unity to optimize script performance. In this example, we create a class called CachedReferences, which leverages Unity's component system efficiently. During the awake method, we retrieve the rigidBody component and store it in a private variable named RB. This single call to getComponent ensures that we don't have to search for the rigidBody repeatedly during each frame update, significantly reducing performance overhead. In the update method, we handle player input through the horizontal axis using input getAxis horizontal. We then apply a force to the rigidBody based on the input received, allowing for smooth and responsive movement. By caching the rigidBody reference, we optimize our script by eliminating the need for repeated component lookups, thus enhancing frame rates and overall game performance, especially in scenarios involving multiple scripts. Utilizing this technique not only streamlines our code but also embodies a best practice in Unity development, paving the way for more complex and efficient game mechanics. Now let's see how we can implement a simple job using Unity's job system. In this example, we define an addition job struct that implements the iJob interface, enabling us to run the addition logic on a separate thread. This struct has two integer inputs, x and y, as well as a native array int to store the result of the addition. The execute method performs the calculation and assigns the sum to the first element of the result array. Next, we create a job system example class that inherits from MonoBehavior. Within the start method, we instantiate a native array int to hold our result and create an instance of addition job, setting the values of x, y, and the result array. After that, we schedule the job for execution using the schedule method, which returns a handle that allows us to track the job's progress. Finally, we call handle complete to ensure the job finishes before accessing the result, logging it, and disposing of the native array to prevent memory leaks. This straightforward implementation not only demonstrates job scheduling but also emphasizes efficient data handling in Unity. Next, we will write the following code to optimize physics calculations in Unity. In this script, we create a class called PhysicsOptimization that will manage the rigidBody component of a game object. We start by declaring a private variable RB to hold the reference to the rigidBody, allowing us to manipulate its properties efficiently. In the start method, we retrieve the rigidBody component attached to the game object and set its isKinematic property to true. This setting prevents Unity from applying physics calculations to the object, vastly improving performance, especially when dealing with multiple objects in the scene that do not need continuous physics interactions, such as static decor. Moving to the update method, we introduce a condition to determine if physics should be enabled at a certain moment. If the condition is met, we set the isKinematic property to false, allowing the rigidBody to start responding to physics simulations when needed. This approach gives you control over when physics interactions occur, optimizing performance and ensuring resource management in your game. Now let's see how we can implement profiling in our Unity projects using the Profiler API. This code snippet begins by utilizing the Profiler begin sample method, allowing us to mark the start of a specific code block that we want to monitor. By enclosing complex logic within this sample, we can gain insights into how that particular section of code affects performance. After executing the required logic, we conclude the profiling with Profiler end sample, which finalizes the sampling period and records data for analysis. By leveraging this technique, developers can identify performance bottlenecks more accurately. It's particularly useful during the development phase, where you can track various parts of your code in real time and adjust them accordingly to optimize performance. Importantly, using profiling markers can provide clarity on frame rates and memory allocations, which are critical metrics in game development. Thus, integrating such profiling practices into your workflow enables a more efficient debugging process and ultimately leads to smoother gameplay experiences for your users. Implementing these best practices in Unity development is critical for building advanced and optimized games. Through effective asset management, object pooling, caching references, utilizing Unity's job system, optimizing physics, and leveraging profiling tools, you can significantly enhance the performance and scalability of your projects. As you practice these techniques, remember that optimization is an ongoing journey. Continuously evaluate and refine your approach as your project evolves, ensuring your game runs smoothly and provides an immersive experience for players. Happy developing! In this lesson, we are going to dive deep into the world of data collection in Unity, focusing specifically on arrays and lists, two foundational data structures that every game developer should master. As we've journeyed so far, we've covered best practices for advanced development in Unity, including asset management, object pooling, and script optimization to enhance performance. We discussed using Unity's job system and the burst compiler for CPU-bound tasks, which allows us to efficiently utilize our resources. Today, we will talk about how to effectively organize and manipulate our game data using arrays and lists. Now let's see how we can implement an array to collect player scores in our game. First, we declare an integer array called scores with a fixed size of 5, allowing us to store up to 5 different scores. This is a straightforward way to manage a specific limited set of data. Next, we can initialize this array with specific values, representing scores from players who have completed challenges within the game. Now let's take a look at how this array can be utilized within a Unity script. We create a class called playerScores that inherits from MonoBehavior, enabling us to attach it to a game object within our scene. Inside the class, we define the scores array initialized with playerScores. When the game starts, the start method is triggered, which contains a loop that iterates through the scores array. For each iteration, it accesses the score of a player using their index and displays it through Unity's debug log method. This efficient use of index-based access allows us to manage and display each player's score seamlessly, showcasing the power of arrays in organizing game data. Now let's see how we can implement a list to manage a player's inventory dynamically. To declare a list in C, we use the list class from the system, collections generic namespace, which allows us to create a flexible collection that can change in size. In this example, we initialize a list of strings called inventory, which will store the names of items that our player collects. Next, we can add items to our inventory using the add method. Here, we add a health potion and a mana potion, demonstrating how easy it is to dynamically grow the list as players collect various items during gameplay. Each time we call the add method, the list expands to accommodate the new entries, allowing for smooth inventory management. Now let's take a look at how we can display the contents of our inventory. We define a method called displayInventory, where we use a for-each loop to iterate through each item in the list. By logging each inventory item to the console, we provide feedback to the player and highlight the ease of accessing and displaying elements stored in a list. This implementation showcases the fundamental benefits of using lists in scenarios where data changes frequently. Now let's see how we can implement a method to allow players to use items from their inventory. This code defines a function named useItem, which accepts a string parameter representing the item the player intends to use. Inside this method, we first check if the specified item exists in the inventory by utilizing the contains method of the list. This is an essential step to ensure that we don't attempt to remove an item that is not present, thereby preventing potential errors. If the item is found in the inventory, the remove method is called to remove it from the list. This dynamic nature of lists allows us to manage inventory items effortlessly, reflecting changes as items are used. Following the removal, we provide feedback to the player using debug log, indicating that the item has been used and removed from their inventory. This not only enhances the player experience by confirming their action, but also helps in tracking inventory state throughout the game. Consequently, this method exemplifies how lists can simplify inventory management through their inherent flexibility, unlike static arrays which do not allow for alteration in size. While both arrays and lists have their places in Unity development, it's crucial to understand their differences. Arrays provide speed with a fixed size, which is often optimal in performance-sensitive applications. Lists, being flexible, come at a slight performance cost due to their resizable nature, but they shine in scenarios where the count of elements isn't known upfront. When designing your game mechanics, consider the data structure that best fits your requirements. Are you maintaining a fixed set of player stats? An array might be perfect. Are you managing a player's inventory that can change as they pick up and use items? A list will be your best friend. Now let's take a look at how we can implement enemy position tracking using an array in Unity. In this code, we define a public class called Enemy Manager that manages the positions of our enemies. We declare an array called Enemy Positions of type vector3 with a fixed size of 5, which allows us to store the positions of 5 enemies. In the start method, we initialize the positions of each enemy using a loop. Here, each position is set to a unique value along the x-axis, spaced apart by 5 units. This demonstrates how arrays provide structured storage for data that has a known limit, in this case, the 5 enemies. Next, in the update method, we use another loop to continuously move each enemy to the right at a constant speed. We achieve this by adding a change in the x-coordinate, calculated with vector3 right time delta time, ensuring smooth movement over time. This code effectively shows how arrays can be utilized in game development for managing multiple objects, making it easy to manipulate their positions in a straightforward manner. Now let's take a look at how we can implement an item management system using a list in Unity. In the given code, we define a class called Item Manager, which is responsible for handling the player's inventory. Inside this class, we create a list of strings named items that will hold the names of the items in the inventory. When the game starts, the start method is invoked automatically, where we call the addItem method multiple times to populate the inventory with a sword and a shield. Each time an item is added, the application logs a message to the console, confirming that the item has been added successfully. This demonstrates how lists can be dynamically updated as the player's inventory changes. Next, we define the displayItems method, which iterates through the items list and prints each item's name to the console, allowing players to see what they have collected. This showcases the flexibility of using a list for inventory management, where adding new items or displaying current ones can be done seamlessly. If, for example, the player finds another sword, we can simply call addItem sword again, and the list will handle it gracefully. In summary, understanding how to wisely use arrays and lists empowers developers to craft robust Unity applications. Arrays offer speed and straightforward access, while lists provide dynamic flexibility for data manipulation. By incorporating these structures into your projects, you'll strengthen your ability to manage game data smoothly and effectively. Make sure to practice creating different data structures as tailored to your game's needs, and as you progress, these fundamental techniques will elevate your development skills. As we wrap up this lesson, remember that mastering data structures is just one aspect of game development. As you continue on your journey, keep practicing these concepts. In the next lesson, we'll delve deeper into more advanced data structures, such as dictionaries and HashSets, which will further expand your toolkit for creating efficient and dynamic game systems. Stay tuned. Now let's take a look at how we can manage player scores using a dictionary in our Player Scores Manager class. Inside this class, we first declare a private member variable, player scores, which is a dictionary that maps an integer key representing the player's ID to an integer value for their score. This allows us to efficiently store and retrieve scores using player IDs as unique identifiers. In the constructor of the Player Scores Manager, we initialize player scores as a new instance of dictionary. This setup is crucial as it prepares our data structure before we attempt to add or manipulate player scores. By organizing scores this way, when we need to add a score for a player, we can quickly check if the player's ID exists in the dictionary. If the ID is not found, we can add a new entry. If it does, we can easily update the existing score. This streamlined approach ensures that managing player scores is quick and efficient, and it avoids the overhead that would come from searching through arrays or lists. Now let's see how we can implement a method to add player scores to our dictionary. This method, addPlayerScore, accepts two parameters, playerID and score. The first step in the method is to check if the player ID already exists in the dictionary using the ContainsKey method. This is important because it allows us to differentiate between adding a new player or updating an existing player's score. If the player ID does not exist, we add the player along with their score to the dictionary, logging a message to confirm the addition. On the other hand, if the player ID is found, we update the existing score and log a different message indicating that the score is being updated. This approach efficiently handles score management without the need to search through a list or array, giving us quick access to player information based on their unique ID. Overall, this method demonstrates the effective use of a dictionary for managing player scores in a game development context. Now let's take a look at how we can retrieve a player's score from our dictionary effectively. We define a method called getPlayerScore, which takes an integer parameter, playerID, representing the ID of the player whose score we want to access. Inside the method, we utilize the tryGetValue function provided by the dictionary. This method is particularly useful because it safely attempts to fetch the score associated with the given player ID without risking key reference errors that could crash our game. If the player ID exists in the dictionary, tryGetValue assigns the corresponding score to the out variable score, and the method proceeds to display the score in the console using debug log. This helps in quickly tracking scores during gameplay. However, if the player ID is not found, the method instead outputs a message indicating that the player ID is not found and returns as a failsafe value. This approach ensures our application remains robust, providing a clear and straightforward way to manage score retrieval, enhancing our game's reliability and user experience. Now that we've gone through adding and retrieving scores, let's discuss how to iterate through all the player scores stored in our dictionary. This process is essential for efficiently displaying information like a leaderboard or debugging statistics. Now let's see how we can implement this functionality. We will create a method named displayAllScores. In this method, we utilize a for-each loop to iterate over each entry in our player scores dictionary. Each entry is a key-value pair, which consists of a key, the player's ID, and a value, the player's score. As we loop through these pairs, we employ debug log to print each player's ID alongside their score. This approach allows for a clear and organized visualization of all player scores in the console, making it a useful tool for any game developer looking to manage and display player statistics effectively. By examining the scores in this manner, we can easily monitor performance and ensure the game's scoring system is functioning as intended. Now let's see how we can implement a simple item collection system using a hash set in Unity. In the item collection class, we first declare a private variable called collected items, which is a hash set of strings. This hash set will hold the names of the unique items that a player collects throughout the game. In the constructor of the item collection class, we initialize the collected items variable, creating a new instance of the hash set. This ensures that our collection is ready to use as soon as an instance of item collection is created. The advantage of using a hash set lies in its ability to automatically manage duplicates. Therefore, we can confidently add items without needing to check if they already exist. By leveraging this hash set, we can efficiently track the items collected by the player throughout their journey. In the next steps, we will explore how to add items to this collection and check their existence, enhancing the gameplay experience by ensuring that each power-up or collectible is stored uniquely, adding depth to the game's functionality. Now let's see how we can implement the functionality to add items to our hash set, ensuring that our collection remains unique. The collectItem method takes a string parameter representing the name of the item to be collected. Within this method, we utilize the add method of the hash set. This method attempts to add the item to the collection and returns true if the addition was successful, indicating that it is a new entry. If the item already exists in our hash set, add returns false, preventing duplicates. We then use conditional statements to provide feedback to the player. If the item is successfully added, the script logs a message indicating the item has been collected. Conversely, if the item was already collected, it informs the player that this item is already in their collection. This approach contributes to a smooth user experience by managing the item collection seamlessly and efficiently, ensuring players are not notified about duplicates, but instead are affirmed of their unique achievements. Now let's see how we can retrieve items from our hash set efficiently by checking for their existence. The method hasItem is designed to determine whether a specific item is already present in the collected items hash set. By using the contains method, it efficiently verifies if the item name provided as a parameter exists in the collection. This approach is optimal for performance-sensitive applications, where rapid checks for item presence are crucial. Instead of focusing on extracting items, which isn't the primary purpose of a hash set, this method offers a quick way to ascertain the status of an item's existence. The Boolean value returned, either true or false, serves as a simple yet powerful tool for managing game states, such as deciding if a player can collect an item again or perform actions related to that item. Utilizing hash sets in such a manner enables cleaner and more effective data management within the game, ensuring a smooth gameplay experience. This technique is integral to keeping track of unique items, such as player collectibles, enhancing the overall interaction and engagement in your game scenarios. Now let's take a look at how we can effectively display all the unique items collected by a player from our hash set. We begin by creating a method called displayCollectedItems, which starts by outputting a header message indicating that we are about to list the collected items. This provides clarity to the player or developer reviewing the logs. The method then utilizes a for-each loop to iterate through each item stored in the collected items hash set. By doing so, every unique item collected is accessed sequentially. Within the loop, we leverage debug log to print each item to the console. This approach is not only straightforward but also efficient, as it ensures that every item is displayed without the risk of duplicates, thanks to the inherent properties of a hash set. Ultimately, this method serves as a valuable tool for giving players a quick and clear overview of their power-ups or items, enhancing their gaming experience by confirming what they have collected. Dictionaries and hash sets both leverage the power of hash tables for quick data access, making them suited for different scenarios. While dictionaries serve well for key-value storage where you want to associate one piece of data with another, hash sets excel at collecting unique items without the concern of duplicates. Referring back to our earlier examples, think about a hypothetical multiplayer game where you need to track player scores as well as which characters each player has unlocked. You can easily use a dictionary to maintain scores, while a hash set could be used to ensure that no character is collected more than once. In summary, both dictionaries and hash sets in Unity provide efficient ways to store and manage game data. Dictionaries allow for quick lookups and updates with key-value pairs, perfect for scenarios requiring direct access based on a unique identifier like player IDs. Conversely, HashSets ensure that collections remain unique, making them ideal for scenarios like item collections or achievement tracking. As your game development skills grow, understanding and effectively implementing these data structures will significantly improve how you manage data, enhance performance, and create engaging gameplay experiences. So make sure to experiment with both structures as you build your games, and don't forget to share your findings. Happy coding and stay tuned for the next lesson. Effective design principles for user interfaces are essential in delivering a seamless and enjoyable experience for players. The essence of effective menu design lies in its ability to guide players smoothly through options and choices, enhancing their overall game experience without overwhelming or confusing them. In today's lesson, we will explore the foundational principles and technical aspects behind crafting compelling and user-friendly menus in Unity, emphasizing the importance of clear layout, intuitive navigation, and aesthetic consistency. So far, we have learned about dictionaries and hash sets in Unity game development, focusing on their importance for managing game data efficiently. We explored how dictionaries allow for quick retrieval and modification of data using key-value pairs, particularly for tracking player scores, while hash sets help maintain unique collections of items. The lesson covered practical implementations for adding, retrieving, and displaying data in these structures. Now we will delve into designing user interface elements, specifically menus, which are critical for guiding players through their gaming experience. Now let's take a look at a simple yet powerful menu manager implementation in Unity. This script establishes the connections between UI buttons and their respective functions, allowing players to interact with the menu effectively. We start by defining public button variables for the essential menu options: starting the game, loading a game, accessing settings, and quitting the game. In the start method, we add event listeners to each button, linking them to specific methods that handle the corresponding actions. For instance, when the start button is clicked, the start game method is invoked, logging a message to the console to indicate that the game is starting. This provides a clear point where you can integrate scene loading logic later. Similar methods are set up for loading a game, opening settings, and quitting the application. Each method demonstrates the feedback or action taken when the button is pressed, maintaining clear communication between the player's input and the game's state. By organizing the code in this manner, we establish a straightforward management system for our menu while ensuring a seamless user experience. Now let's implement a simple back navigation feature for our settings menu. In this code, we use two game objects to represent our menu panels, one for the settings panel and another for the main menu panel. When a player chooses to access the settings, the open settings method is called, setting the settings panel to active and the main menu panel to inactive. This creates a clear transition that helps players understand their current context within the game. Conversely, when the player wants to return to the main menu, they can invoke the back to main menu method, which reverses this process. It deactivates the settings panel and reactivates the main menu panel. This straightforward toggle mechanism not only simplifies navigation, but also enhances the player's control over their experience, ensuring they can switch between different menu options with ease. By maintaining a clean interface and clear transitions, players will feel more oriented, minimizing confusion as they navigate through the menus. This is essential for effective user experience and can significantly impact player engagement in your game. Now let's take a look at a key component that helps maintain aesthetic consistency in our UI menus. The Style Manager class is designed to manage the styling of various UI elements in your game, ensuring a cohesive look that matches your overall theme. Within this class, we start by defining public variables for the UI elements we want to customize: an image for the background panel, a color for that panel, a text field for the title, and a font for the title text. In the start method, we invoke the applyStyles method, which sets the visual properties of these elements when the game begins. The applyStyles method is where the magic happens. It assigns the specified color to the background panel, applies the chosen font to the title text, and ensures the text remains legible by setting its color to white. Additionally, we specify a font size to help it stand out. This approach allows for easy updates to the visual style by simply changing the variables assigned in the Unity inspector, making it easy to adapt the aesthetic as your game evolves. Now let's take a look at the Fade Manager class, which is designed to handle smooth fade transitions of UI elements. This script utilizes Unity's Canvas Group component, which allows us to control the visibility of UI panels by manipulating their alpha values. The Fade Manager includes two public methods, fade in and fade out, which initiate the fade effect. When called, these methods start a coroutine named fade2, passing in the desired target alpha value, one for fully visible and 0 for completely transparent. Inside the fade2 coroutine, we define the process for the fading effect. We track the starting alpha and use a loop to gradually change the alpha value over a specified duration, which in this case is set to 1 second. Through linear interpolation with math, lerp, we achieve a smooth transition as the elapsed time advances. This enhances the user experience by making transitions between different menu screens feel polished and responsive. In the end, we ensure the Canvas Group's alpha is set to the target value, guaranteeing that the UI appears correctly once the fade is complete. This approach not only improves visual feedback, but also makes navigating the menu system more enjoyable. Now let's implement a simple volume control using a slider, which enhances player interaction and customization. This script begins by importing essential namespaces, UnityEngine and UnityEngine, UI allowing us to work with UI elements like sliders. We define a public class named Volume Control, which will manage our slider. Within this class, we declare a public slider variable called Volume Slider, which will link to the UI component in our scene. In the start method, we set the initial value of the volume slider to match the current audio volume of the game. This provides an intuitive experience for players, as they will see the slider reflect the existing volume level when they enter the settings. Additionally, we register a listener that triggers the set volume method when the slider value changes, enabling real-time adjustments to the game's audio. The set volume method itself takes a float parameter, volume, which represents the new value from the slider. Whenever players interact with the slider, this method updates the audio listener's volume property accordingly. This seamless interaction not only empowers players to manage sound levels, but also reinforces their engagement in the gaming experience. As we round up our discussion on menu design principles, remember that quality UI design is about more than just looks. It's about creating a cohesive experience that guides players seamlessly through your game. By understanding the principles of effective layout, intuitive navigation, aesthetic consistency, and functional interactivity, you will equip yourself with the tools to craft captivating menus that enhance your game's overall experience. In summary, today we covered the critical aspects of designing effective user interfaces for games. We discussed the importance of layout, navigation flow, aesthetic consistency, and interactivity in menus. As we continue on our journey through game development, we'll refine these skills and explore even more complex UI systems to bring our games to life. Feel free to engage with these concepts in your upcoming projects, and remember that practice is key to mastering these principles in Unity. Happy developing! Let's dive into the exciting world of interactive components for menus in game development. Today, we'll explore how these components enhance player engagement and streamline navigation through your game interface. Interactive components are the lifeblood of any user interface, allowing players to perform actions intuitively and efficiently. So far, we've learned about the significance of effective user interface design in enhancing player experience within games. We covered foundational principles such as logical layout, intuitive navigation, aesthetic consistency, and functional interactivity in menu systems. The lesson emphasized practical implementations within Unity, including code examples for managing menu interactions and visual styling. As we proceed, we will build upon these concepts to bring our menus to life with interactive components. Now let's see how we can implement a basic menu system using buttons in Unity. In this script, we create a class named MainMenu, which defines 3 public buttons for starting the game, opening the settings, and quitting the game. When the scene starts, the start method initializes these buttons to listen for click events. We achieve this by adding listeners to each button that call their respective methods when clicked. The start game method simply logs a message indicating that the game is starting. In a full implementation, you would replace this log with the logic to load the game scene. The Open Settings method also logs a message when the settings menu is opened, which is where you would implement further UI interactions for players to adjust their settings. Finally, the Quit Game method is straightforward. It logs that the game is quitting and then calls application quit to close the application. This structure makes it easy for players to navigate the menu, providing a seamless experience tailored for user interaction. Now let's take a look at how we can implement a volume slider in Unity to enhance our game's audio settings. In this script, we use the slider component from Unity's UI system to allow players to dynamically adjust the audio volume during gameplay. First, we define a public slider variable called volume slider, enabling us to connect our UI slider component to the script through the Unity editor. Next, in the start method, we initialize the slider's value to match the current audio volume referenced by audio listener volume. This ensures that when players open the settings menu, the slider reflects their current volume level. We also attach an event listener to the slider's onValueChanged event, which triggers the adjust volume method whenever the slider is moved. This method takes the slider's current value as a parameter and updates the audio listener volume accordingly, providing instant feedback to the players. Additionally, we log the adjusted volume level to the console for debugging purposes. This implementation creates an intuitive way for players to customize their audio experience, making the gameplay more immersive and engaging. Next, we will implement a simple toggle switch for managing sound settings in our menu. The sound toggle class begins by declaring a public toggle variable, sound toggle, which will link to the toggle control in our UI. In the start method, we set the toggle's initial state based on the current audio volume. If the volume is non-zero, the toggle is checked, indicating that sound is enabled. To make the toggle functional, we attach an event listener to the sound toggle that calls the toggle sound method whenever the toggle's value changes. This method takes a Boolean parameter, isOn, reflecting the toggle's state. Inside toggle sound, we adjust the audio listener volume property. If the toggle is checked, the volume is set to 1, enabled. If unchecked, it is set to 0, muted. This instant feedback not only allows players to customize their audio experience easily, but also provides a clear log message indicating whether the sound has been enabled or muted, enhancing user interaction and satisfaction within the menu system. Now let's implement a dropdown for selecting the game difficulty, which simplifies the options players have to choose from. In this script, we start by declaring a public variable for the dropdown component, which allows us to link it to the UI element in the Unity editor. The start method is essential as it initializes our dropdown. It adds a listener that triggers the change difficulty method whenever the selected value changes, enhancing interactivity. Next, we populate the dropdown with options by clearing any existing selections and creating a list of difficulty levels: easy, normal, and hard. The addOptions method is used to insert these options into the dropdown, with normal set as the default value to provide a balanced starting point for players. When a player selects a different difficulty, the change difficulty method is called, where we retrieve the text of the selected option and log it for debugging purposes. This connection between the dropdown and the game logic not only streamlines user experience but also maintains clarity, allowing players to easily adjust their gameplay settings without overwhelming choices. Now let's implement the following code to create a comprehensive settings menu that leverages multiple interactive components. This script begins by defining several public UI elements: a button for returning to the main menu, a toggle for sound settings, a slider for volume control, and a dropdown for selecting gameplay difficulty. In the start method, we set up event listeners for each component, ensuring that they respond appropriately to user interactions. For instance, when the back button is clicked, it triggers the back to main menu method, providing a smooth transition back to the main menu. The sound toggle and volume slider are linked to their respective methods to adjust audio settings dynamically, enhancing the user's control over their experience. Moreover, the populate dropdown method clears any existing options in the dropdown and populates it with a fresh list of difficulty levels, from easy to hard, defaulting to normal. This structure allows players to seamlessly select their preferred difficulty, demonstrating how to effectively combine various UI components for an engaging user experience. Each interaction is logged to the console, providing feedback that reinforces the sense of control and immersion within the gameplay environment. At the heart of effective menu systems lies the balance between aesthetics and functionality. While immersive designs are vital, they must also serve practical purposes. By integrating interactive components, you create an inviting space where players can engage effortlessly with your game. The smoother the interaction, the more enjoyable the experience. As we wrap up, remember that user interface design is a key piece of the gaming puzzle, shaping how players perceive and enjoy your game. Through buttons, sliders, toggles, and drop-downs, you can create a dynamic environment that empowers players with control and personalization. Take the principles we discussed today and apply them to your projects. Test different combinations of interactive components to discover unique solutions tailored to your gameplay. Practice makes perfect, and every tweak gets you closer to an aesthetically pleasing and functional user interface. Happy developing, and remember, the key to engaging menus is the seamless blend of user interaction and design. Embarking on the exploration of Unity's physics engine marks the beginning of an exciting journey into the art of game development. Understanding how physics operates in Unity is essential for crafting dynamic environments where objects behave realistically. Today, we will dive into the core components of Unity's physics system: rigid bodies, colliders, and physics materials. As we explore these concepts, we aim to equip you with the tools you need to make your game worlds vibrant and engaging. So far, we have learned about the importance of interactive components in game menu systems, covering practical implementations in Unity that enhance player experience. Today, we will focus on the foundational aspects of Unity physics, including object interactions, forces, and how to create an immersive gameplay experience through physical simulation. Now let's take a look at how to set up a rigid body component for a game object in Unity. In this script, we first define a private variable to hold our rigid body instance. The start method is then utilized, which runs at the beginning of the object's lifecycle, ensuring that our rigid body is initialized as soon as the game object is instantiated. Inside the start method, we add a rigid body to our game object using GameObject-add-component-rigid-body. This line creates a new rigid body component which is necessary for physics-based interactions. We then assign properties to the rigid body. Setting the mass to 5F determines the object's weight, while a linear drag of 1F introduces resistance to its movement, causing it to slow down over time. Additionally, we set the angular drag to 0.5F, controlling how quickly the object can stop spinning when forces are applied. Lastly, by enabling gravity through RB, use gravity equals true, we ensure that our object will be affected by the global gravity settings in Unity, allowing it to fall naturally within the game world. This foundational setup is key to creating dynamic interactions in your game. Now let's see how we can implement a box collider to define the physical boundaries of our game object. In the script, we begin by declaring a class called colliderSetup, which inherits from monoBehavior. This enables us to use Unity's various built-in functionalities. Next, we define a start method that Unity calls when the game object is initialized. Inside this method, we use add-component-box-collider to dynamically attach a box collider component to our game object. This is crucial because colliders are essential for collision detection, allowing our object to interact with other colliders in the physics environment. We then configure the isTrigger property of the box collider. By default, it is set to false, meaning it will act as a physical barrier, preventing other colliders from passing through it. However, if we need the collider to act as a trigger, where it detects overlaps without causing physical responses, we can set isTrigger to true. This flexibility allows for varied gameplay mechanics, enhancing how a game object interacts with the environment and other objects within the Unity scene. Now let's take a look at how to implement a physics material in Unity through C# code. In this script, we begin by creating a new instance of the physics material, which allows us to customize the physical properties of the material that our game object will use. We set three key properties: dynamic friction, static friction, and bounciness. The dynamic friction, valued at 0.2, represents the resistance experienced when the object is in motion, allowing for smoother sliding on surfaces. The static friction of 0.6 determines the resistance when the object is stationary, helping it remain in place until a sufficient force is applied. Next, we configure the bounciness at 0.8, which allows objects to rebound energetically when they collide, enhancing gameplay elements like jumping or bouncing off surfaces. After setting up these properties, we retrieve the collider component attached to our game object. If a collider exists, we apply the physics material to it. This step ensures that the dynamic interactions defined by our material take effect during gameplay, allowing for a more immersive experience as players interact with different surfaces in the game. Now let's implement a script that demonstrates how to apply forces and rotations to a rigid body in Unity. First, we start by establishing a reference to the rigid body component within the start method. This is essential because it allows us to manipulate the object's physics properties throughout the game. Next, in the update method, we check for player inputs. By detecting when the spacebar is pressed, we can apply a forward force to the rigid body. The add force method is utilized here, taking in a vector that multiplies the forward direction vector 3 forward by a specified magnitude, which in this case is 500. This creates an impactful push on the object. Additionally, we handle another input, where pressing the T key triggers the add torque method. This method applies a rotational force around the apaxis vector 3 up, enabling the object to spin. The torque magnitude of 200 creates a pronounced rotation effect. By modifying these force values, you can fine-tune the dynamics of how your object moves and interacts, enriching your gameplay experience with responsive and engaging controls. Now let's explore how to implement custom gravity behavior in our game using Unity. The script begins by defining a custom gravity class that derives from monobehavior, allowing it to be attached to game objects within the Unity scene. Inside this class, we declare a private variable RB, which will hold a reference to the rigid body component of the game object. In the start method, we initialize RB by retrieving the rigid body component attached to the game object. This step is crucial because it enables us to manipulate the object's physical properties later. Here we also set the global gravity of the physics environment to a downward force represented by the vector new vector 3, 0 minus 9.81 F0. This configuration simulates Earth-like gravity, pulling all objects downwards. Moving to the update method, we introduce input handling to allow the player to interact with the game. Specifically, we check if the spacebar is pressed, and if so, we apply an impulsive upward force to the rigid body, effectively simulating a jumping action. By adjusting the force value to vector 3 up 10F, we provide the necessary upward acceleration that enables the character to leap into the air, demonstrating how we can create dynamic movement through gravity manipulation. Now let's take a look at how we can handle collision detection using Unity's physics system. The code showcases a simple monobehavior class that utilizes the onCollisionEnter method. This method is automatically called when a collider attached to the game object. This script is attached to makes contact with another collider during a collision event. Within the onCollisionEnter method, we receive a parameter called collision, which contains information about the colliding object. By checking the tag of the collided object with compare tag obstacle, we can determine if it is an obstacle we want to interact with. If the collision involves an obstacle, a message is logged to the console indicating the collision has occurred. This feedback is critical for gameplay mechanics, as it can be the foundation for more complex interactions, such as applying damage or triggering animations in response to the collision. Thus, this snippet forms the basis for developing engaging gameplay elements where the player receives immediate visual or audio feedback based on their interactions within the game world. As we've navigated through these essential aspects, you're now equipped with the foundational knowledge of Unity's physics engine. With rigid bodies, colliders, physics materials, forces, and collision detection explained, you can begin to craft more immersive and interactive gaming experiences. In summary, we explored how to set up essential components to create physical interactions, utilize forces to influence object behavior, and effectively manage collision events. Moving forward, we will delve into enhancing your game character animations, linking their movements to the physical interactions we've established, taking your game development skills to the next level. Prepare to bring your characters to life with dynamic movements and responsive controls that align seamlessly with the physics that populate your game world. Creating advanced character animations in Unity involves mastering sophisticated features like inverse kinematics, IK, and blend trees. These techniques empower game developers to craft intricate and dynamic character movements, enhancing overall gameplay experience. So far, we learned about the foundational components of Unity's physics engine, including rigid bodies, colliders, and physics materials, which are essential for creating realistic game dynamics. We explored how rigid bodies allow objects to respond to forces and gravity, while colliders define their physical boundaries for collision detection. Additionally, we discussed the significance of physics materials in fine-tuning object interactions and demonstrated how to apply forces and handle collision events. With this knowledge, we are now prepared to enhance character animations and integrate responsive controls into our game development projects. Now let's implement a script that will allow our character's foot to adapt to uneven terrain using inverse kinematics. This script utilizes the onAnimateIK method, which Unity calls automatically for IK calculations during animation. First, we define a reference to the animator component and two transforms, one for the foot and another for a ground check. The ground check will help us determine if the foot should be placed on the ground. We also specify a layer mask to identify which layers represent the ground. Within the onAnimateIK method, we begin by performing a raycast from our ground check reference point directly downwards. If the raycast detects a surface, the character's foot position and rotation are adjusted accordingly using the setIK position and setIK rotation methods. This allows the foot to align perfectly with the ground beneath it, providing realistic placement during movement. If the raycast does not hit any surfaces, we disable the IK position and rotation weights for the foot, ensuring that the character's animations remain fluid without any unnatural foot placement. This approach not only enhances the realism of the animations, but also improves the overall responsiveness of the character to the environment. Next, we will implement the character movement script that enables our character to move based on player input while integrating smoothly with the previously defined blend tree for animation. This script begins by declaring two public fields, an animator reference and a float variable called speed to capture the character's movement pace. In the update method, we read the player's input on the vertical axis, which typically corresponds to the WS or up-down arrow keys. This input value is stored in the speed variable, allowing us to determine how fast the character moves. The absolute value of speed is then passed to the animator using the setFloat method, which adjusts the speed parameter defined in the blend tree. By doing this, we enable the animated transitions between the walk and run states, depending on how fast the player is pressing the movement keys. Finally, we translate the character's position forward based on the speed, multiplied by time delta time to ensure smooth movement consistent with the frame rate. This combination of input handling and animation blending creates an immersive experience as the character transitions fluidly through different animations in response to player controls. Now let's see how we can implement a comprehensive character control system that utilizes both inverse kinematics, IK, and a blend of animations for a more immersive experience. The Advanced Character Control class serves as the core for handling the character's animations and movements. It includes references to the animator and the positions of the left and right foot transforms, along with a ground check mechanism. These references allow the character to adapt its foot placements dynamically based on the terrain. In the onAnimateIK method, we invoke the placeFoot function for both feet, applying IK adjustments to ensure they align accurately with the ground. During the update method, we capture input from the player to control forward movement. The speed from the player's input is mapped to the animator's speed parameter, which triggers animations accordingly. The character moves by translating its position based on the determined speed while leveraging the blend tree for smooth transitions. Finally, the place foot method is responsible for detecting the ground beneath each foot using a raycast. It sets the position and rotation of the feet based on the surface they are placed on, ensuring that the animations remain responsive and visually cohesive, particularly during complex movements across uneven terrains. Now let's implement the following arm follow object script, which offers a simple mechanism for having a character's arm dynamically follow a target object during gameplay. First, we define two public variables: target object, which represents the object that the arm will aim towards, and rig, which is a reference to the animation rig used for control. In the start method, we check if the rig is set and enable it by setting its weight to 1, allowing the rig's influences to take effect. This is crucial for ensuring that any constraints we want to use will operate correctly. Next, within the update method, we continuously check if the target object is set. If so, we calculate the direction from the arm's current position to the target's position, which allows us to determine how the arm should rotate. Using quaternion, look rotation, we create a rotation that aligns the arm toward the target based on this direction. Finally, we apply this rotation to the arm transform, ensuring it smoothly adjusts its angle to face the target object. This simple yet effective method can enhance character interactions, making it feel responsive and engaging as it follows the player's cues or environmental signals. Now let's take a look at how we can implement animation events in Unity to enhance gameplay mechanics. The Sword Attack class defines a method called Perform Attack, where we can include the logic for dealing damage to enemies during a sword slash. This method is designed to be called at a specific point in the animation by utilizing Unity's animation event feature. To set this up, you would first select the sword attack animation clip in the animator window and add an event at the precise moment when the sword makes contact with the target. This ensures that the actions such as applying damage occur exactly when the animation depicts the strike. By logging a message to the console, sword slashed, deal damage, we can verify that the method is being triggered correctly during gameplay. This synchronization between animation and game logic not only promotes a seamless experience for players, but also enhances the overall feel of character actions, making them more impactful and realistic. By mastering animation events, you can develop more engaging gameplay experiences that react fluidly to player interactions. As we wrap up our discussion on advanced character animation techniques in Unity, remember that these tools, inverse kinematics, blend trees, animation rigging, and animation events, are designed to enhance the realism and engagement in your character animations. By implementing these techniques, you can create sophisticated character behaviors that respond dynamically to your game environment, allowing players to immerse themselves fully in the experience. In conclusion, learning to harness these advanced features will push your game development skills to new heights, transforming static animations into dynamic interactions. So dive in, experiment with these techniques, and let your characters move with purpose and precision in the beautiful world you're creating. And remember, practice makes perfect, so don't be afraid to break things as you learn. Happy animating. Asynchronous programming is a fundamental technique that enables game developers to maintain high responsiveness and smooth gameplay, even while running complex and resource-intensive operations. Today, we're going to dive into the exciting world of asynchronous programming in Unity. We'll explore how this approach keeps our games agile and responsive, allowing us to create memorable experiences without compromising performance. So far, we covered advanced character animations in Unity, including techniques like inverse kinematics and blend trees that enhance movement realism and gameplay integration. Now, we'll talk about how asynchronous programming enables smooth interactions in real-time environments, highlighting the significance of non-blocking code execution. Now let's implement an asynchronous asset loading method by creating a coroutine. This coroutine, named loadAssetAsync, begins by calling resources loadAsync, which initiates the process of loading a game object without blocking the main thread. This means that your game can continue operating as it waits for the asset to load, ensuring a seamless experience for players. While the asset is being loaded, the coroutine checks a property called load is done. If the loading is still ongoing, the coroutine yields control back to Unity for the next frame, using yield return null. This allows the game to keep running smoothly, rendering graphics and processing user inputs without any interruptions. Once the loading is complete and load is done becomes true, we retrieve the loaded asset, cast it to a game object, and you can proceed to utilize that asset in your game. This approach keeps your game responsive even during potentially heavy resource loading operations, demonstrating the power of asynchronous programming in enhancing the player experience. Now let's see how we can implement a coroutine to smoothly move a game object across the screen. The moveObject coroutine begins by accepting three parameters: the starting position, the ending position, and the duration of the movement. Inside the coroutine, we initialize a variable elapsed time to track the time taken for the movement. We use a while loop that continues running until elapsed time exceeds the specified duration. During each iteration, we update the object's position by using the vector3lerp function. This function creates a smooth transition between the start and end positions based on the progress calculated by dividing elapsed time by duration. To ensure our movement is frame rate independent, we increment the elapsed time by time delta time, which represents the time since the last frame was rendered. By yielding null, we pause the coroutine's execution until the next frame, allowing other processes in the game to run. Finally, we ensure the game object reaches its exact ending position by explicitly setting transform position to end after the loop completes. This method results in a fluid animation that enhances the player's experience seamlessly. Now let's see how we can implement asynchronous player data fetching using Unity's UnityWebRequest. This coroutine, named FetchPlayerData, is designed to retrieve player information from a remote server without freezing the game. First, we create a UnityWebRequest instance that requests data specific to the player's ID. Inside the using statement, we ensure that this web request is properly disposed of once it completes, preventing memory leaks. The coroutine then yields while the request is sent and awaited. This means the game's main loop remains unaffected, allowing it to continue running smoothly. After waiting for the response, we check the result of the request. If there's an error, it's logged for debugging purposes. Conversely, if the request is successful, we pause the received JSON data into a playerData object using Unity's built-in JSON utility. This received data can now be processed further, such as updating game states or displaying information to the player. By structuring the network request in this manner, we provide a seamless online experience, crucial for keeping gameplay fluid and engaging. Now let's implement a system to manage our coroutines effectively to avoid issues like overlapping executions. The code defines a coroutine reference called currentCoroutine. In the startMyCoroutine method, we first check if current coroutine is not null, meaning that another coroutine is currently running. If that's the case, we use stopCoroutine to terminate the existing coroutine before proceeding. This guarantees that we don't unintentionally have multiple instances of the same coroutine running simultaneously, which could lead to unexpected behavior and performance problems. After stopping any existing coroutine, we assign currentCoroutine to the result of startCoroutine initiated with your desired coroutine method. This structured approach ensures that our coroutine management remains clean and efficient, promoting better performance and reducing potential bugs. By managing the life cycle of coroutines in this way, we foster a smoother gameplay experience, preventing issues that could arise from starting multiple coroutines without properly handling their states. This is a crucial best practice for maintaining effective asynchronous operations in Unity. As we wrap up our discussion on asynchronous programming in Unity, it's clear that adopting non-blocking code execution methods transforms game development, allowing for rich and responsive gaming experiences. By leveraging coroutines, we gain powerful control over asynchronous operations and effectively create smoothly flowing gameplay. In this video, we covered the essentials of non-blocking code execution, explored practical use cases in Unity, and pinpointed best practices for implementing asynchronous programming. Remember that the goal is to maintain a seamless gameplay experience, keeping players engaged without interruptions. Embracing asynchronous programming is not merely an enhancement, it's a necessity in crafting modern games that resonate with players. Now, as we move forward, get ready for our next lesson where we will dive into optimizing game performance further, enhancing your toolkit as a Unity developer. Stay tuned. Achieving optimized Unity scripts requires a holistic approach encompassing continuous profiling, adherence to coding standards, and consideration for scalability. In this video, we will explore the importance of optimizing scripts for performance, ensuring your games not only run smoothly but also efficiently. So far, we learned about asynchronous programming in Unity, which is crucial for maintaining smooth gameplay without interruptions. We explored the use of coroutines for non-blocking code execution, exemplified through asset loading and network requests. Additionally, we discussed best practices for managing coroutine lifecycles to prevent performance issues. Moving forward, we will delve into optimizing game performance to enhance our development skills. Performance optimization is an essential skill for any game developer. It can greatly affect not just how fast your game runs but also how enjoyable it is for players. Optimizing scripts might seem daunting, but it largely revolves around a few key principles. Understanding how Unity operates under the hood, making efficient use of data structures, and avoiding common pitfalls in game development. Now let's see how we can implement a common, yet inefficient way of checking for enemy collisions within our Unity game. The code iterates through a list of enemies in every frame, calculating the distance from each enemy to the player using the vector3distance function. If the distance is less than a predefined detection radius, the game will trigger the appropriate response to handle enemy detection. While this approach may work adequately with a small number of enemies, it can become costly in terms of performance as the number of enemies increases. This is because the loop runs on every frame, resulting in repeated distance calculations for each enemy. As the enemy count grows, the CPU has to spend more time executing this operation, which can lead to noticeable performance degradation. To optimize this process, we should consider alternatives such as spatial partitioning or using colliders for detection, which significantly reduces the number of checks performed each frame. This transition not only enhances performance but also ensures smoother gameplay, allowing players to enjoy their experience without lag or stuttering. Now let's see how we can implement a basic grid-based system for optimized collision detection using the grid class. This class serves as the backbone for spatial partitioning by maintaining a collection of cells, each designed to store references to nearby enemies. Within the grid class, the cell struct contains a vector that holds pointers to enemy objects, effectively segmenting them based on their positions. The constructor initializes a specified number of cells and sets the size of each cell, allowing us to delineate the game world into manageable sections. Next, the addEnemy function is crucial for populating these cells. It calculates the appropriate cell index using getCellIndex, which takes an enemy's position and determines which cell it belongs to based on its coordinates. This is performed using the cell size, optimizing the organization of enemies into their respective grid cells. Furthermore, the getNearbyEnemies method retrieves only those enemies that are within the same cell as the given position, significantly improving the efficiency of collision checks. By limiting our checks to nearby enemies instead of the entire list, we can enhance performance and streamline gameplay interactions. Now let's take a look at how we can implement object pooling for projectiles to enhance performance in Unity. The projectile pool class serves as the foundation for managing a collection of reusable projectiles. We start by declaring a vector that holds pointers to the inactive projectiles, which allows for efficient memory management. Next, we define the getProjectile method. This method checks if there are available projectiles in the pool. If the pool is empty, it will create a new projectile using the createNewProjectile method. Otherwise, it retrieves the lost projectile from the pool, removes it from the pool, activates it, and returns it to the caller. This mechanism ensures that we minimize the overhead of frequent memory allocations. When a projectile is no longer needed, the return projectile method is called. This method deactivates the projectile and adds it back to the pool rather than destroying it. By reactivating objects instead of continually instantiating and destroying them, we drastically reduce the amount of memory allocation and garbage collection required during gameplay. This ultimately leads to smoother performance and a better experience for players. Now let's take a look at how we can manage timed events in Unity using coroutines. The provided code demonstrates the implementation of a coroutine called timed event, which takes a float parameter for the delay duration. By utilizing the yield return new wait for seconds delay statement, the coroutine pauses execution for the specified amount of time without blocking the main game loop. This is particularly useful for actions that should occur after a certain delay, such as spawning enemies or triggering animations at specific intervals. When the time delay has elapsed, the code flows to the next line, where you would typically place the actions to execute following the wait period. This method allows you to orchestrate events in your game seamlessly, enhancing the user experience while keeping the game responsive. By employing coroutines in this way, you can prevent frame rate drops associated with heavy calculations performed in the update method, illustrating an effective technique for optimizing performance in Unity. Now let's see how we can implement proper initialization in Unity using the awake and start methods. In Unity's mono behavior, the awake method is called when the script instance is being loaded, making it ideal for setting up references and initializing variables before other scripts start. It is recommended to keep the operations performed in awake, lightweight to avoid affecting startup times. Next, we transition to the start method, which is invoked just before any of the update methods are called for the first time. This is where we can handle tasks that require the game to be fully initialized, such as loading assets. By using a coroutine for asset loading, we avoid blocking the main execution flow of the game, enabling smoother gameplay experiences. The load assets coroutine allows for deferred execution of the asset loading process without stalling the frame, making it a practical choice for operations that could take considerable time. This cautious separation of responsibilities between awake and start enhances both performance and script organization, leading to a more efficient and enjoyable game development experience. As you develop your game, refactoring becomes an essential practice. Clean, maintainable code isn't just a code principle, it's a performance principle. By ensuring your scripts are organized and modular, you facilitate easier updates and optimizations. Refactor heavy scripts into smaller components or classes. Breaking down responsibilities allows us to optimize individual components without risking unintended side effects elsewhere. For example, separating UI logic from gameplay mechanics will give you the flexibility to optimize each part independently. Consider a player character's functionality. Instead of encapsulating all movement, shooting, and an inventory system into a single class, break them into dedicated classes like player movement, player shooting, and player inventory. This approach enables you to optimize each class individually, simplifying debugging and performance enhancements in the long run. Now let's take a look at a common design pattern used in Unity development, the singleton pattern, which ensures a class has only one instance and provides a global access point to that instance. In this implementation, the Game Manager class is defined with a static method, getInstance, which serves as the entry point to access the singleton instance. This method utilizes a static local variable, ensuring that the instance is created only once and remains available throughout the application's lifetime. The constructor of the Game Manager is private, preventing other classes from creating new instances of Game Manager, thereby enforcing the singleton behavior effectively. Additionally, both the copy constructor and the assignment operator are deleted to prevent copying and assignment operations, which could lead to multiple instances and compromise the intended design. By managing the game state through a single instance of Game Manager, we streamline logic and enhance performance, avoiding unnecessary duplications of objects and ensuring consistent behavior throughout the game. This approach makes your game more efficient while providing a centralized structure for managing critical game elements. In conclusion, Optimizing scripts is a multifaceted process that requires consistent effort and a strategic approach. By profiling your code, managing memory wisely, and refactoring regularly, you can greatly improve the performance of your Unity projects. Remember that optimization isn't just about making your game run faster, but also about creating a more enjoyable experience for your players. So from profiling to memory management, we've covered the essentials of optimizing scripts in Unity. As you progress in your game development journey, keep these principles in mind, and you'll become adept at spotting and resolving performance issues. Thank you for joining this lesson. In the next video, we will explore how to implement graphics optimizations to improve visual fidelity without sacrificing your game's performance. Stay tuned for more exciting content. Let's dive right into the fascinating world of integrating artificial intelligence, AI, into Unity. This topic bridges cutting-edge technology with creative game development, enabling developers to create intelligent and engaging gameplay experiences. Today, we will explore the essential concepts, tools, and techniques needed to incorporate AI into your Unity projects effectively. So far, we learned about the importance of performance optimization in Unity, covering key principles such as profiling, efficient memory management, and the use of object pooling. We discussed techniques like spatial partitioning for collision detection and the benefits of coroutines for managing frame updates. Additionally, we emphasized the significance of code organization and adhering to coding standards to simplify refactoring and enhance performance. In this lesson, we will focus on AI integration, starting from the fundamentals and progressing toward advanced applications like pathfinding and behavior trees. Now let's take a look at how we can implement a basic AI pathfinding algorithm in Unity. This script defines a pathfinding class that manages the search for the most efficient route from a starting node to a target node using two lists, an open set and a closed set. The open set contains nodes that need to be evaluated, while the closed set holds nodes that have already been evaluated. At the start of the game, the script initializes these lists and adds the starting node to the open set. During each game update, the script checks if there are nodes to evaluate. If so, it identifies the node with the lowest total cost, given by the getLowestFCost node method, and evaluates it. If this current node is the target, the script calls retracePath to trace the optimal route back to the start. As the algorithm explores neighboring nodes, it calculates the cost to reach them. If a neighbor is walkable and not in the closed set, the script updates its cost values and sets its parent to the current node, adding it to the open set if it hasn't been evaluated yet. This continuous process allows NPCs to navigate dynamic environments intelligently. Now let's see how we can implement a behavior tree for an NPC that can switch between patrolling and chasing a player. We begin with defining a PatrolGuard AI class, where we establish the behavior tree in the start method. Here we initialize a new behavior tree instance, setting up the root node as a selector node. This structure prioritizes actions, allowing the NPC to evaluate conditions dynamically. Next, we create two sequence nodes. The patrol node, which contains actions that check if the NPC is in the patrol area and moves along its designated path, and the chase node, which initiates a chase when the player is detected. By adding both the patrol and chase nodes as children of the root, we allow the NPC to first assess whether to patrol or chase based on its current state. Throughout the game loop in the update method, we call tree tick to process the behavior tree. This method executes the relevant actions based on current conditions, enabling the NPC to effectively respond to player interactions and environmental changes, resulting in more engaging gameplay. Now let's implement the following code to define an intelligent non-player character using Unity's ML Agents toolkit. We start by creating a class NPC agent that inherits from agent. In the onEpisodeBegin method, we can establish the initial state of our NPC, preparing it for training or gameplay scenarios. Next, we move to the collect observations method, where we gather relevant environmental data for the agent to inform its decision-making process, enhancing its ability to act intelligently in various conditions. Following this, the onActionReceived method is crucial, as it processes the actions that the agent takes based on the predictions from the trained model. This action handling is vital for implementing learned behaviors in real time, making the NPC responsive and adaptive. Lastly, we include the heuristic method, which allows for manual control if needed, providing developers with an option to test the agent's behavior without machine learning input. Combining these elements, this framework enables our NPC to learn and improve through experience, aligning with the overarching goal of enhancing gameplay dynamics in Unity. Now let's take a look at the Decision Throttling AI script, which implements a decision-making system that respects performance constraints by introducing a cooldown mechanism. This script is crucial for maintaining smooth gameplay while ensuring that non-player characters, NPCs, engage dynamically with player actions. In the script, we define a class Decision Throttling AI, which inherits from monobehavior, allowing it to be attached to game objects. Here we start by declaring a player transform and setting a cooldown period, which establishes how frequently the AI can make decisions. The update method checks if enough time has passed since the last decision was made by comparing the current time with the stored last decision time. If the cooldown period has elapsed, the make decision method is invoked. Within make decision, the AI determines its action based on the distance from the player. If the player is within a specified proximity, the AI outputs a signal indicating it is hiding, which illustrates a defensive behavior. Conversely, if the player is further away, the AI opts to seek, demonstrating an active pursuit strategy. This approach effectively balances AI interaction complexity with performance, enhancing gameplay immersion without compromising frame rates. In summary, the integration of AI technologies into Unity significantly enhances gameplay experiences, improving interactivity and narrative depth. We've explored foundational concepts, from pathfinding and state management to advanced machine learning strategies, empowering developers to craft sophisticated NPC behaviors. As AI continues to evolve, leveraging Unity's comprehensive AI tools will play a pivotal role in shaping the future of interactive entertainment. Embrace these techniques to not only elevate your Unity projects, but also to contribute meaningfully to the ever-changing landscape of game design. Are you ready to implement what you've learned? Get out there, experiment, and see how AI can transform your game ideas into realities filled with life and interactivity. In today's lesson, we'll delve into advanced NPC behavior techniques, exploring how behavior trees can elevate your game's artificial intelligence by providing a modular approach to decision-making. So far, we've learned about integrating artificial intelligence, AI, into Unity, focusing on performance optimization, pathfinding, and behavior trees. We explored the application of algorithms like A for NPC navigation, and discussed designing NPC behaviors using behavior trees for more realistic interactions. Additionally, we touched on utilizing machine learning techniques with Unity's ML Agents toolkit to create adaptive characters. Overall, AI integration not only enhances interactivity, but also enriches the storytelling and gameplay experience. Let's jump right into it and expand our understanding of behavior trees, which is a powerful tool for managing complex NPC behaviors. Unlike traditional state machines, which can become unwieldy as you add states, behavior trees offer a more elegant solution by allowing you to create reusable nodes. This modular approach simplifies complex decision-making and enables flexibility for behavior additions or modifications, creating a more dynamic and responsive game world. Now let's implement a simple behavior tree for our NPC to manage patrolling and chasing based on the player's position. We start by defining an unnamed state to categorize the two behaviors, patrolling and chasing. In the start method, we initialize the NPC's state to patrolling. As the game progresses, the update method runs continuously, checking the current state and executing the behavior accordingly. While in the patrolling state, the NPC will call the patrol method to follow a designated path. Crucially, it monitors the player's proximity through the canCPlayer method, which uses the vector 3 distance to determine if the player is within the specified chase distance. If the player is detected, the NPC's state is switched to chasing, where it actively pursues the player. Conversely, if the player is no longer visible, the NPC reverts back to the patrolling state. This basic structure not only showcases the NPC's decision-making capabilities, but also illustrates how behavior trees enable dynamic responses to player actions, making NPCs feel more interactive and lifelike in the game environment. Now let's implement a simple behavior tree for our NPC using C#. This script establishes an enum called state, which defines the two primary states of the NPC, patrolling and chasing. We initialize the current state to patrolling in the start method, setting the stage for our NPC's default behavior. In the update method, we employ a switch statement to determine the current state of the NPC and execute the appropriate behavior. During the patrolling state, the NPC will continuously invoke the patrol method and check if the player is within range using the canCPlayer method. If the player is detected, the state transitions to chasing. Conversely, while in the chasing state, the NPC will call the chase method and revert to patrolling, if the player is no longer visible. The canCPlayer method calculates the distance between the NPC and the player, enabling adaptable behavior based on proximity. This structuring allows for a clean, manageable implementation of NPC behavior, encapsulating state transitions effectively and providing a foundation for further complexity and enhancements. Now let's implement the Patrol with Waypoints script, which enhances our NPC behavior by allowing it to navigate between predefined waypoints. This script introduces a simple yet effective means for an NPC to patrol a designated area. Initially, we define an array of waypoints that the NPC will follow with an integer to track the current waypoint. In the update method, we continuously check the distance between the NPC's position and the current waypoint. When within close proximity, the NPC transitions to the next waypoint, utilizing the modulo operator to loop back to the beginning once it reaches the end of the array. This ensures a seamless patrolling cycle. Furthermore, to introduce a realistic delay at each waypoint, we invoke a coroutine that pauses execution for 2 seconds before the NPC proceeds to move towards the next waypoint. The move to waypoint method is responsible for steering the NPC towards its target, employing Unity's vector3 move towards to calculate its new position based on a defined patrol speed. This method maintains smooth movement while keeping the performance intact. Overall, this code allows for an engaging patrol behavior that can be expanded further with additional complexities, such as varying wait times or different movement patterns at waypoints. Now let's implement the following script for detecting noise made by the player, which will play a critical role in modifying the NPC's behavior based on environmental interactions. In this script, we define a public Boolean variable, isPlayNoisy, which will signal whether the player is making noise, such as running or firing a weapon. The update method serves as the core of this script, where you'll eventually incorporate logic to determine if the player is producing any noise. This persistent checking allows the game to react in real time to the player's actions. The detectNoise method returns the state of isPlayNoisy, providing other components of the NPC's system access to this crucial information. It enables the NPC to evaluate whether to engage in a more aggressive or alert behavior, thus enhancing the NPC's responsiveness and making gameplay more dynamic. By integrating this noise detection into the behavior tree, we can craft scenarios where NPCs are not only aware of the player's visibility but also their auditory signals, leading to more immersive and interactive gameplay experiences. Now let's implement a script that introduces adaptive behavior to our NPC. We begin by declaring a private integer variable, failed chases, which keeps track of how many times the NPC has failed to catch the player. In the update method, we first check if the NPC can see the player. If it can, an attempt to chase the player is made by calling the chasePlayer method. This method simulates a success rate for the chase, returning true or false based on a random value, where a return value of false signifies a failed attempt. When the chase attempt fails, the failed chases counter is incremented, and we proceed to call modify behavior based on failures. This method is crucial as it checks if the number of failures has reached a threshold of 3. Upon reaching this threshold, the NPC modifies its behavior, perhaps by increasing its alertness or changing its strategy, such as looking for cover or preparing an ambush. Lastly, the counter is reset to 0, allowing the NPC to start the evaluation process again. This adaptive mechanism makes the NPC's interaction with the player more dynamic and engaging, enhancing the overall gameplay experience. As we conclude, we've seen the artistry behind creating advanced NPC behaviors using behavior trees. This flexible modular approach not only improves decision-making, but also encourages a rich and immersive gaming experience. Every node in the tree can connect various actions, allowing characters to respond to player actions intelligently. By layering behaviors with sequences and conditions, developers can craft more engaging and believable interactions within their games. The lessons on integrating AI into Unity have opened doors to enhance storylines, gameplay, and interactivity. The beauty of behavior trees lies in their adaptability and how easily they can be modified and expanded over time, making them a fantastic tool in your game development arsenal. So, as you experiment with your own NPC designs, consider how you can use these advanced techniques to create behaviors that feel organic and responsive to player actions. Immerse your players in a world where characters don't just exist, they react, learn, and evolve alongside the gameplay. Dive in, create your own AI, and surprise your players with NPCs that truly live within their game. In the dynamic realm of multiplayer game development, understanding the fundamentals of networking in Unity is essential. Networking allows players to connect and interact within the same game world, creating engaging multiplayer experiences. Today, we'll explore the basics of networking in Unity, covering key concepts, components, and practical code examples to get you started on building your own multiplayer game. So far, we learned about advanced NPC behavior techniques using behavior trees to enhance artificial intelligence in games. We covered the basic structure of behavior trees, including root, action, condition, and composite nodes, and examined how to implement a simple patrol and chase behavior in Unity. Additionally, we explored the integration of conditions like noise detection and adaptive strategies to allow NPCs to learn and modify their behaviors based on player actions. Overall, these techniques contribute to creating dynamic and engaging gameplay experiences. Now, we will cover the fundamental concepts of Unity's networking capabilities, focusing on how to create a basic multiplayer setup. Now let's see how we can implement the core functionality of our Network Manager. In this code, we create a class named MyNetworkManager that inherits from Unity's Network Manager. First, we set the default scenes for offline and online gameplay using the Network Manager's singleton instance. This is crucial as it defines which scenes will load based on whether the game is being played offline or online. Next, we override the onStartServer method. This method is automatically called when the server starts, allowing us to insert any custom server initialization logic. In our case, we log a message to the console to confirm that the server has started successfully. Logging such messages is useful for debugging, as it ensures that our server is up and running. Keep in mind to replace offline scene and online scene with the actual names of the scenes you've created for your game's offline and online modes. By properly setting up the Network Manager like this, you'll have a robust foundation for managing player connections and gameplay across the network. Now that we've established our Network Manager, let's implement player spawning. First, we define a public variable, player prefab, where we can assign our player prefab in the Unity inspector. This prefab must be configured with a network identity component to ensure it functions correctly in a networked environment. Next, in the start method, we set the player prefab of the singleton instance of Network Manager to the one we've defined. This step allows the Network Manager to recognize which prefab it should use for instantiating player objects when clients connect. The real magic happens when we override the onServerAddPlayer method. This method is automatically called by the Network Manager for each client that connects. Here, we instantiate the player prefab and then add it to the client's connection using the network server addPlayerForConnection method. By doing this, whenever a new player joins the game, their corresponding player object is automatically spawned in the game world, allowing them to interact with other players seamlessly. This setup is crucial for creating an engaging multiplayer experience, ensuring every new player has their own character available in the game as they connect. Next, we will implement the player movement functionality within our multiplayer setup. In this code, we first inherit from network behavior, which is essential for all networked objects in Unity. We define a public variable speed to control the player's movement speed. Within the update method, we check if the current instance is the local player using the isLocalPlayer property. This ensures that only the player that owns the character can control its movement. As we capture the player's input, we obtain the values from Unity's input system corresponding to horizontal and vertical axes, allowing the player to move in multiple directions. With this input, we create a movement vector and utilize transform, translate to apply the calculated movement to the player's position, ensuring the movement is frame rate independent by multiplying by time delta time. This approach ensures that all input and movements are handled client-side while allowing the server to maintain control over the player's position, facilitating synchronized movement across all clients in the game. Now let's see how we can implement synchronized movement for our players in a networked environment using Unity. First, we declare the PlayerController class, inheriting from network behavior to enable network functionality. The speed variable sets how fast the player can move. In the update method, we first check if the current instance is the local player, ensuring only the player controlling their character can input movement commands. Next, we capture the player's input using input getAxis for horizontal and vertical movements. Instead of moving the player directly, we now call the CMDMove method, which is marked with the command attribute. This indicates it will execute on the server when invoked by the client, establishing server authority over player movement. The CMDMove method takes the horizontal and vertical input parameters, creates a movement vector, and translates the player's position based on that vector multiplied by speed and time delta time. This approach not only maintains authority but also ensures that all players see consistent positional updates across the network. This model aids in synchronizing player movements, thus enhancing the multiplayer experience. Now, let's implement the method to handle player disconnections in our networked game. We will add an override for the onServerDisconnect method in the MyNetworkManager class. This method is crucial for maintaining a responsive multiplayer experience, as it enables the server to react when a player unexpectedly leaves the game. Within this method, we first log a message that indicates the address of the disconnected player. This information is valuable for debugging purposes and helps in understanding player behavior during sessions. After logging, we call the base class's onServerDisconnect method, which ensures that any necessary cleanup processes specific to Unity's networking framework are executed. This might include removing the player's character from the game world and updating any relevant game state. You might also consider extending this functionality by implementing additional logic, such as notifying other players in the game of the disconnection or updating the user interface to reflect the player's absence. This approach not only keeps the game environment coherent, but also enhances the overall player experience by ensuring that all participants are aware of changes in the game's state. Now that you have a foundational understanding of networking in Unity, covering the basics of the network manager, player spawning, movement synchronization, and managing disconnections, let's touch briefly on some advanced topics that can enhance your multiplayer game experience. For example, you might want to implement a chat system where players can communicate with each other. This requires the use of a networked messaging system. Unity provides the network client send and network server send to all methods to facilitate message broadcasting. You can create a simple chat manager using Unity's UI system combined with network messaging. When a player sends a chat message, you call a command to send the message to the server, which then broadcasts it to all connected clients. This will encourage player interaction and enhance the multiplayer experience. To wrap up, developing multiplayer games in Unity requires a solid understanding of networking principles. We covered the setup of the network manager, player spawning, movement synchronization, and graceful disconnections. As you build your games, consider exploring additional features like matchmaking, authority management, and player interactions. Just remember that networking can be complex, but don't worry. With practice, you'll be able to create immersive multiplayer experiences. Start small, gradually implement features, and always test thoroughly with multiple clients to ensure everything works seamlessly. Happy networking. Network latency and security are two pivotal challenges in multiplayer game development. Addressing these factors is crucial to creating a seamless gaming experience that players will enjoy and trust. In this session, we will dive into effective strategies for managing network latency and enhancing security in your multiplayer games. So far, we learned about the fundamentals of networking in Unity, focusing on the network manager as the core component for connecting players and managing multiplayer interactions. We established player spawning, movement synchronization, and handled disconnects to ensure a smooth multiplayer experience. Additionally, we discussed advanced topics such as implementing a chat system to enhance player interaction. This foundation sets the stage for building dynamic and engaging multiplayer games. Now let's take a look at a simple implementation of a player jump action that includes basic network synchronization. In the provided code, we define a player controller class that extends network behavior, essential for managing networking features in Unity. The jump force variable determines how high the player can jump, while the isGrounded boolean tracks whether the player is on the ground, critical for preventing double jumps. During the update method, we check if the player is local, has pressed the jump button, and is grounded. If all conditions are met, we call the cmd jump command, which is sent to the server to ensure secure handling of the jump action. This setup utilizes the Unity networking framework for clear client-server communication. Within the cmd jump method, we call RPC jump, instructing all clients to execute the jump action. The RPC jump method is marked with the client RPC attribute, meaning it triggers the jump behavior on all connected clients. This design allows players to see their characters jump immediately in response to their actions, effectively reducing perceived latency while maintaining consistency across the game. Now let's see how we can implement interpolation to smooth the movement of non-local players in our multiplayer game. The player controller class begins by storing the target position for where the player should be moving. When the scene starts, we initialize target position to the player's current position. In the update method, we check if the player is the local instance. If so, we handle their movement directly. For non-local players, we use the vector3 smooth damp method to interpolate their position towards the target position. This function takes three parameters: the current position, the target position, and a reference to the velocity, which allows for smooth transitions without abrupt changes. Next, we define a command called cmdMove, which is executed on the server when a player moves. This command updates the target position on the server side. For local players, handle movement captures input from the user and calculates a new position based on that input. This new position is sent to the server using cmdMove, and the local target position is immediately updated to reflect the local player's movement, maintaining synchronization in a smooth manner. This approach significantly reduces visual jitter during gameplay, even under variable network conditions. Now let's implement a basic authentication system to securely handle player logins. We will begin by creating an Authentication Manager class, which is responsible for managing the authentication process. This class has a private variable to store the authentication token received from the server. Next, we will define the startAuthentication method, which takes a username and password as parameters. This method starts a coroutine that handles the authentication request asynchronously. Inside the coroutine, we will create a www form to package the username and password, enabling us to send these credentials to a designated URL on our server. Now let's see how we can handle the server's response. Using Unity Web Request, we will send the request and await a response. If there is a connection error or protocol error, we will log an authentication failure. On the other hand, if the request is successful, we will retrieve the token from the response and log a success message, which can then be used for future validation during gameplay. This approach not only aids in secure player data management, but also enhances the overall security framework of the multiplayer experience. Now let's explore how server-side authorization can enhance security in multiplayer games. In the provided code, the CMD pickup item command is initiated by the player when they attempt to pick up an item. This command first checks if the action is valid by calling the canPickUpItem function. Here, we perform crucial validation checks to ensure that the player is within an acceptable distance from the item they wish to interact with. This is key because it prevents scenarios where players can exploit the game mechanics from unauthorized positions. If the validation is successful, the server then executes RPC pickup item, a client RPC which synchronizes the item pickup across all clients. This means that once the server validates the action, it communicates to all clients that the item has been picked up, ensuring consistency in the game state. By keeping critical game logic such as item pickups on the server side, we significantly reduce the potential for cheating, creating a fairer gaming environment. This approach exemplifies best practices for network security, emphasizing the importance of validating client actions to prevent exploits. Additionally, it is worthwhile to consider encrypting sensitive data in transit. Using transport layer security, TLS, ensures that any data sent between the client and server is encrypted, reducing the chances of interception or tampering by malicious actors. For Unity networking frameworks like UNet or Mira, consider deploying these security layers at the transport level. As you implement TLS, you will typically focus on establishing a secure connection during initial client-server communication. While the implementation details can vary based on your backend setup, the fundamental idea is to ensure that any sensitive authentication or player data remains obscured during transmission. Lastly, always remain proactive about testing for security vulnerabilities. Regularly conduct penetration testing and apply security patches to your game server. You may even consider employing player reporting mechanisms within your game, which can help you identify potential cheaters or exploiters based on player feedback. This encourages a safer environment for everyone. In summary, network latency and security are paramount to providing an enjoyable multiplayer gaming experience. By implementing prediction systems, interpolation for smoother movements, robust authentication protocols, server-side validation, encryption, and a culture of security mindfulness, you can create an engaging game that players trust to be secure and responsive. As you continue developing your multiplayer games, remember that addressing these challenges isn't just about creating a fun experience. It's about building a community that values fair play and security. Happy gaming, and may your next multiplayer project be a resounding success. Effective memory management is essential in Unity game development. It ensures smooth performance, prevents issues like stuttering or crashes, especially on resource-constrained platforms, and maintains a great user experience. In this lesson, we will delve deeply into optimizing memory management within Unity, focusing on practical techniques to enhance performance and stability in games. So far, we covered the critical role of network latency and security in multiplayer game development. We explored effective strategies for managing latency through predictive input and interpolation to enhance player experience. Additionally, we discussed the importance of secure player authentication, server-side validation, and data encryption to mitigate vulnerabilities. This knowledge lays the groundwork for creating engaging and trustworthy multiplayer games. Now we will talk about optimizing memory management in Unity, covering techniques such as garbage collection management, object pooling, and efficient memory allocation. Now let's see how we can optimize object position management in Unity to alleviate garbage collection pressure. In the first example, we have a typical scenario where a new Vector3 object is created every frame within the update method. This approach can lead to excessive memory allocations, as Unity's garbage collector will need to clear these temporary objects, resulting in frame rate drops during gameplay. To improve our handling, we switch to modifying an existing variable called currentPosition, which we initialize in the start method. Instead of instantiating a new Vector3, we simply update the x-coordinate of our currentPosition variable. By doing this, we avoid creating new memory allocations each frame, significantly reducing the workload on the garbage collector. The update method is now more efficient, as it continuously modifies and assigns the existing position to the transform of our game object without incurring the overhead of generating temporary objects. This method ultimately results in smoother gameplay and improves overall performance, particularly in scenarios where update is called frequently. Now let's see how we can implement object pooling to optimize memory usage in our Unity projects. The Object Pool class serves as a manager for reusable game objects, specifically projectiles in this case. We begin by declaring a public game object field for the projectile prefab that we want to pool and a queue to hold our inactive projectiles. In the start method, we pre-instantiate a set of projectiles. Here, we create 10 instances of the projectile prefab, deactivate them, and add them to the queue. When we need to fire a projectile, we can utilize the getProjectile method. This method checks if any inactive projectiles are available in the pool. If so, we retrieve one from the queue, activate it, and return it for use. However, if the pool is empty, we instantiate a new projectile as a backup. To return the projectile back to the pool once it's no longer needed, we can call the releaseProjectile method, which deactivates the projectile and enqueues it for future reuse. This approach significantly reduces memory allocations during gameplay, thereby enhancing overall performance and minimizing garbage collection overhead. Now let's see how we can implement effective memory management using the using statement in C#. This statement is particularly important when dealing with idisposable objects such as file streams. By utilizing the using statement, you ensure that resources are properly disposed of once they are no longer needed, which helps prevent memory leaks, an issue that can severely impact performance in Unity. In the given code, we instantiate a file stream object, which opens a file for reading or writing. The using statement encompasses the operations performed on the file stream, ensuring that once the block of code is executed, the file stream is automatically closed. This automatic management is crucial because it efficiently frees up unmanaged resources, such as file handles, that could otherwise continue to consume memory if not disposed of correctly. By consistently using the using statement whenever you work with idisposable objects, you enhance the reliability of your code while simultaneously optimizing memory management. This practice not only contributes to smoother gameplay but also enriches the overall user experience in your Unity projects. Now let's see how we can implement asynchronous scene loading using Unity's built-in functionality. In the provided code, we start by defining a coroutine method called loadYourScene, which utilizes the scene manager's loadSceneAsync method to load a new scene called YourSceneName without freezing the game. This is crucial for maintaining a smooth user experience, as it allows the game to continue running while the new scene is being loaded in the background. Within the coroutine, we create an asyncoperation variable, asyncload, that keeps track of the loading process. Next, we use a while loop to check the status of asyncload. As long as the scene is not fully loaded, indicated by asyncload is done being false, we yield return null, which tells the coroutine to wait until the next frame before continuing. This approach allows the game to remain responsive during the loading phase, enhancing player experience during scene transitions. By employing this technique, you can ensure that players are not left waiting, thus creating a more enjoyable and seamless experience as they move between different parts of your game. Now let's implement caching to optimize performance by minimizing repetitive calculations within the game. In the code, we start by declaring a private variable cached vector, which will hold the result of a complex vector calculation. Within the update method, which is called once per frame, we assign the value of cached vector by calling a method calculateComplexVector. This approach is beneficial because it allows us to compute the complex vector once, reducing unnecessary calculations in subsequent frames. By caching the calculated value, we improve efficiency and decrease the memory overhead associated with creating temporary objects. Finally, we set the transform position of the game object using the value stored in cached vector. This process ensures the position is updated with the computed vector, leading to smoother gameplay and less pressure on the system. By reusing values and minimizing calculations, we're not only enhancing performance but also improving the overall experience for the player, especially in situations where the calculation is resource-intensive. In conclusion, Effective memory management in Unity is an ongoing commitment that involves using tools available in Unity, such as the Profila for tracking memory usage, implementing object pooling, managing garbage collection judiciously, and optimizing assets. These practices can help maintain smooth gameplay, prevent crashes, and ensure that players enjoy a seamless experience. As we wrap up this lesson, remember that optimizing memory management not only enhances your game's performance, but also contributes to a more enjoyable experience for players. The techniques discussed are essential for creating games capable of running efficiently across the many devices players may use, ultimately leading to a higher quality product. Keep experimenting with these strategies in your Unity projects, and you'll see notable improvements in performance and user satisfaction. Profiling is the cornerstone of effective game optimization, providing essential insights into performance issues that could hinder a game's smooth operation. Today, we're diving deep into the world of profiling techniques in Unity. So far, we learned about effective memory management in Unity, emphasizing the importance of optimizing memory to enhance performance and stability in games. We discussed critical techniques such as minimizing garbage collection, implementing object pooling, and managing memory leaks. Additionally, we explored the role of asset management and caching in reducing memory usage and maintaining smooth gameplay. These practices are essential for delivering an engaging user experience in Unity game development. Now we will cover the vital profiling techniques that can help us nail down those pesky performance bottlenecks in our games. Profiling in Unity starts with understanding the toolset available to us. One of the most powerful tools is the Unity Profila, which provides a comprehensive look into your game's performance. With this handy tool, you can monitor the CPU, GPU memory usage, rendering, and other important metrics that contribute to your game's performance. By gathering real-time data, you can identify resource hogs and focus optimization efforts where they matter most. Let's take a closer look at how to access and utilize the Unity Profila. To get started with the Unity Profila, simply navigate to the window menu at the top of the Unity interface, find the Analysis submenu and select Profila. Once opened, you'll see a wealth of information laid out in a series of graphs and metrics. At the top, you'll see timelines representing CPU usage, memory allocation, rendering statistics, and more. Clicking on different panels allows you to delve into specific areas of performance. Don't forget to check the Record button to ensure you're collecting data from your game while it's playing. Next, we'll take a look at how textures are loaded and their potential impact on memory management in Unity. In the provided example, we begin by loading a background texture using the resources load method within the start function. This approach allows us to dynamically access assets stored in the resources folder, which is useful for loading assets as needed during gameplay. However, it's crucial to recognize that once this texture is loaded, it remains in memory unless explicitly unloaded. In the update function, we have a comment indicating that the texture is not being unloaded during scene transitions. This oversight can lead to memory leaks where textures accumulate in memory and are not freed, consuming valuable resources. To manage memory effectively, it's important to implement a strategy for unloading unused assets once they are no longer needed. For instance, we could use the resources unload unused assets method to clean up any textures that are not being utilized, thereby preventing unnecessary memory consumption and ensuring a smoother experience for the player. Next, let's see how we can optimize our CPU performance by modifying a method that relies on complex calculations. In the initial implementation, the update method executes a loop that performs an expensive calculation for each iteration, leading to longer execution times as it computes square roots and sine values in every frame. This repeated computation can significantly affect the game's performance, especially if it runs for multiple frames. Now let's implement an improved version of this code using a caching strategy. By introducing a dictionary to store previously calculated results, we can avoid redundant calculations when the input value remains unchanged. The getCachedValue method first checks if the result for a given integer is already available in the cache. If it is not, it performs the complex calculation, stores the result in the cache, and then returns it. This caching mechanism ensures that each unique result is computed only once, which dramatically reduces CPU usage in the update method. As a result, when utilized in a performance-heavy environment, this approach leads to smoother gameplay as the system focuses its resources more efficiently. Next, we will look at how to optimize the rendering of transparent objects to reduce overdraw and improve GPU performance. The first part of our code showcases the onRenderObject method, which is responsible for rendering each transparent object in the scene individually. Within a loop, it calls a function to draw each object based on the number of transparent objects identified. While this approach ensures that all intended objects are rendered, it can lead to inefficiencies, particularly when many transparent objects overlap, as the GPU will need to process each one separately. Now let's see how we can enhance this rendering process by implementing a batching mechanism. The second part of the code introduces the drawBatchTransparentObjects method. Here, instead of processing each transparent object individually, we gather all relevant objects into a single batch and utilize graphics, drawMeshInstanced. This function allows us to render multiple instances of the same mesh with a single draw call, significantly reducing the overhead associated with multiple draws. By adopting this static batching approach, we can effectively lessen the strain on the GPU, leading to improved performance and smoother frame rates. The profiler will reflect these optimizations by illustrating a reduction in overdraw and a more efficient rendering process. Now let's implement a custom profiling utility using System Diagnostics stopwatch to measure the performance of specific operations within your game. This method allows us to track how long intensive tasks take, enabling us to gather valuable data that can highlight performance bottlenecks. In the given snippet, we define a method called measurePerformance. First, we instantiate a stopwatch object, which is a valuable tool for measuring elapsed time in a highly accurate manner. We then invoke the start method on the stopwatch, marking the beginning of the operation we want to measure. Next, we execute a potentially heavy operation, such as perform heavy calculation, where you would place any task you want to analyze. After the operation completes, we call stop on the stopwatch, which records the time taken for the operation. Finally, we log the elapsed time in milliseconds using debug log, providing concrete evidence of how long the calculation required. By utilizing this simple approach, you gain insights into specific pieces of your code, allowing for targeted optimization based on the timing data collected. This custom profiling method can be especially useful in identifying and refining performance-critical areas of your game. Don't forget about the power of the Unity Profiler's user interface. Learn to navigate it effectively to gain insights into your performance metrics visually. Switch between deep profiling for granular performance analysis and the default mode for an overarching view of your performance landscape. As your project evolves, routinely revisit the profiler to monitor the changes made and ensure optimizations keep your game on the right track. Remember that the key to effective profiling is iteration. After you adjust and optimize your game based on the insights gathered, always reprofile to observe the impacts of your changes. Performance is rarely perfect after a single run. Continuous refinement is crucial. In conclusion, mastering profiling techniques is essential for any Unity developer aiming to optimize their games. The Unity Profiler offers a robust toolkit for assessing various performance metrics, from memory allocations to CPU and GPU usage. By leveraging these insights, you can effectively identify and eliminate bottlenecks, creating a smoother gameplay experience for your users. So go ahead, dive into the profiler today and uncover the hidden performance secrets within your game. Happy profiling! Let's dive into the essentials of game concept and planning, an exciting phase that sets the stage for your entire game development journey. It's crucial to establish a solid foundation through careful planning and conceptualization before you're about to dive into development. So far, we've learned about effective techniques for memory management, optimizing game performance, and the importance of profiling in Unity. Now, we will cover the essential steps of conceptualizing a game idea, defining its scope, and planning your development milestones to ensure a successful journey in creating your game. When it comes to initiating your game development endeavor, the first task is conceptualizing your game idea. This moment is pivotal, acting as the blueprint that will guide all subsequent efforts. You'll want to brainstorm various ideas, thinking about what sets your game apart from a crowded market filled with competitors. Crafting a distinctive theme, whether it's a majestic fantasy world, a dark dystopian realm, or a bright urban environment, is essential for grabbing players' attention. For example, envision a whimsical fantasy world where the sky is a vibrant shade of candy pink, quite a visual treat. However, creating that visual isn't just about aesthetics, it also requires understanding core gameplay mechanics. So ask yourself, what will players be able to do? How will they interact with the game world? Let's say for a 2D platformer, core mechanics might revolve around running, jumping, and collecting magical jewels while dodging fierce enemy blobs. A clear game vision is vital to your planning phase. One effective way to crystallize this vision is through documentation. Consider creating a concept summary. This is like a compact elevator pitch, articulating your game's essence within a few sentences. Here's an example based on our whimsical platformer concept. Welcome to Jewel Quest, a vibrant 2D platformer where players dash through beautifully animated levels, collecting sparkling jewels while avoiding quirky antagonists. This summary succinctly highlights the game's premise and core mechanics, providing both a clear vision and a compelling narrative hook that players will find intriguing. Once you've anchored your game concept, you'll want to refine your ideas further into a game design document, GDD. This document is your roadmap, outlining essential features, art style, narrative elements, and more. Think of it as your game's guiding scripture, evolving as your project progresses but invaluable for keeping the team focused and on track. A well-crafted GDD should include sections on gameplay mechanics, character design, user interface, level design, and audio-visual elements. You'll refer back to this document frequently as the basis for discussing ideas with your team. For demonstration purposes, here's a simple GDD snippet for our game, Jewel Quest. Game Overview ***, a lively 2D platformer where the player collects jewels and defeats blob enemies to progress through levels. Main character ***, a brave young adventurer with the ability to dash, jump, and float for short distances. Goal ***, collect jewels within a time limit while overcoming obstacles and enemies. With a solid game idea and design document in place, you can now move to defining the project's scope and milestones. This step entails aligning your ambitious vision with the practical realities of resources, timelines, and team capabilities. Begin by assessing your resources and timeframes, considering your team's skill set and any budget constraints. One strategy is to break down your game concept into manageable components. Let's say, in our 2D platformer, this means identifying core elements such as player movement, enemy behavior, level design, and collectibles. Crucially, you'll also want to set achievable development milestones. These act as checkpoints that help you assess progress and make necessary adjustments along the way. Early milestones could include creating a basic prototype, while later ones might involve integrating graphics and sound, followed by extensive playtesting. But how do you prevent feature creep? The infamous tendency for new features to sneak into your project, leading to scope bloat. Regularly review your project's scope. Stay focused on core gameplay elements and be willing to cut or postpone new features that don't add significant value to your game. Aim for a cohesive experience by acknowledging that sometimes less is more when it comes to gameplay features. To illustrate, let's take a look at milestone setting for Jewel Quest. 1 Milestone 1 ***, complete the initial game prototype with basic mechanics. 2 Milestone 2, implement player collectible mechanics and basic enemy behavior. 3 Milestone 3 ***, integrate art assets and create the final level layout. After defining the scope of your game project, the next critical step is selecting the appropriate genre and platform. Choosing the right genre shapes your game's narrative and mechanics significantly. With our platformer, we must focus on rigorous control designs, level structure, and player navigation mechanics. A role-playing game, on the other hand, would emphasize story depth and character development. In parallel, the platform dictates technical requirements and potential market reach. Each has its own unique aspects. For PC gaming, you might leverage widespread hardware capabilities, while console or mobile platforms require more tailored approaches. Assess your resources again here. Align your genre and platform so that they bolster your project vision and enhance accessibility for players. Now let's implement the following code to manage basic player movement and jumping mechanics in our 2D platformer. This script utilizes Unity's rigid body-to-D component, which is essential for any physics-based interactions, allowing us to simulate realistic movements. We begin by initializing a rigid body-to-D instance in the start method, which is executed once at the beginning. This gives our player a physical body that can respond to forces. The update method is where we handle player input continuously. It captures horizontal movement using the Unity input system, allowing players to move left and right seamlessly. To handle jumping, we check if the player is grounded and if the jump key spacebar is pressed. Upon these conditions being met, an upward force is applied, propelling the player into the air. The grounding check is performed through collision detection with ground objects, updating a boolean to signify if the player can jump. With this structure, we ensure smooth and responsive controls that enhance gameplay, allowing players to navigate the world deftly. This foundational mechanic is critical, setting the stage for further enhancements like collectibles and enemy interactions. Now let's take a look at how we can manage collectible items in our game using a C# script. Within this script, we utilize Unity's onTriggerEnterTD method, which detects when another collider enters the trigger collider attached to the collectible object. This is essential for implementing item pickups in our game. When the player character, tagged as player, intersects with the collectible, the script activates the logic for collecting the item. Here, we use the compareTag method to ensure that we only respond to the player's interactions, ensuring other colliders do not affect the collectible's behavior. Once the item is confirmed to be collected, the script calls the destroy method to remove the collectible from the game world. This creates a satisfying mechanic for players, as it provides instant feedback that an item has been successfully gathered. Implementing this script helps reinforce the game's core mechanics, enhancing player engagement as they interact with collectibles throughout the levels. Moving on, once the mechanics are tested and refined, you'll integrate them into comprehensive levels shaped by thoughtful design. Each section designed in Unity's scene editor can leverage prefabs to maintain consistency and ensure the whole game feels coherent. In conclusion, planning and conceptualizing your game are foundational steps in the development process. By carefully defining your game idea, its scope, and setting clear development milestones, you create a structured pathway to guide your journey from concept to playable game. Keep iterating, experimenting, and refining your mechanics to craft an interactive experience that captivates players. Next, we will delve deeper into the exciting world of asset integration and level design, ensuring our game world feels fully realized and engaging for players. Happy developing! The final stage of game development is dedicated to polishing and testing, necessary for refining the game and enhancing the player experience. This phase ensures that all the hard work put into the game design, programming, and art comes together seamlessly to provide players with an enjoyable gaming experience. So far, we learned about the importance of game concept and planning in setting a strong foundation for development. We've discussed techniques for memory management, performance optimization, and the steps involved in conceptualizing a game idea, including documentation and creating a game design document (GDD). Additionally, we've highlighted the necessity of defining project scope, setting milestones, and selecting the right genre and platform to enhance the gameplay experience. Now we will cover polishing techniques, playtesting methodologies, and debugging practices to ensure your game is in peak condition before its launch. Polishing involves refining and tuning various elements of the game to ensure that everything runs smoothly. This process isn't just about fixing bugs. It involves improving graphics, refining mechanics, enhancing user interfaces, and making the game overall more enjoyable. Think of this step as adding the final coat of paint to a beautifully crafted piece of furniture. One significant aspect of polishing is ensuring that the user interface, UI, is user-friendly and aesthetically pleasing. A cluttered or confusing UI can turn players off, no matter how engaging the gameplay is. Now let's implement a script to manage the menu interactions in our Unity game. The menu controller class serves as the backbone of our user interface, specifically for handling the actions related to the Start button. Firstly, we declare a public variable Start button, allowing us to assign a button from the Unity inspector, establishing a link between our script and the UI element. In the Start method, we set up an event listener for the button, which will trigger the Start game method whenever the button is clicked. This interaction is crucial as it initiates gameplay and transitions the player to the main game scene. The Start game method executes the scene transition using the Scene Manager load scene function, where we specify the name of the scene to load. This is typically where the main gameplay occurs. By integrating this functionality, we ensure a smooth transition from the menu to the game, enhancing the user experience. Through this intuitive setup, we streamline the player's journey, making it straightforward to dive into the action with just a click of a button. Now let's take a look at a script that implements sound effects for collectible items, enhancing the audio experience in your game. This script defines a class called Collectible, which is responsible for managing what happens when a player interacts with a collectible object. First, we declare a public variable to hold the audio clip for the collect sound. This allows you to assign the specific sound effect you want to play through the Unity inspector. Next, we need to create a private variable to store the audio source, which is responsible for playing back audio. Within the Start method, we use getComponentAudioSource to initialize our audio source component, ensuring it can produce sound at the right moment. The real magic happens in the onTriggerEntityD method. This method checks for collisions with other objects, specifically looking for when the player enters the collider attached to our collectible. If the object tagged player collides with the collectible, the sound effect plays using PlayOneShot, giving instant feedback to the player. Finally, the collectible object is destroyed, effectively simulating the item being picked up. This integration of sound and gameplay greatly enhances immersion, making the experience more engaging. Now let's see how we can implement a unit test for the player health system in Unity. In our example, we create a class called PlayerHealthTest that uses the NUnit testing framework. Within this class, we define a method annotated with the test attribute, which indicates that it should be executed as a test. This method, named TestPlayerTakesDamage, simulates a scenario where the player takes damage. First, we instantiate a new player object. We then call the takeDamage method on this instance, passing in a value of 10, which represents the amount of damage the player is supposed to take. To validate that the player's health adjusts accordingly, we utilize the assert equal method, comparing the expected value of health 90 to the actual health value after the damage is applied. This assumes that the player starts with 100 health. By running this test, we can ensure that the logic behind health reduction is functioning correctly. Implementing automated tests like this not only helps catch issues early, but also boosts confidence in the robustness of the code as we approach the final stages of game development. Next, we will write a simple integration test for verifying that a player can collect points when an item is collected in the game. This is essential to ensure that the scoring system updates correctly during gameplay. In the code, we define a class called GameIntegrationTest using the NUnit framework, which is designed for creating and running tests. Within this class, we create a method named PlayerCollectsPoints marked with the test attribute to indicate that it is a test method. Here we first initialize a new instance of the game class, a player instance, and an item that provides 10 points when collected. The heart of this test lies in the line where we simulate the action of the player collecting an item through the game's method, PlayerCollectsItem. This action occurs within the context of gameplay, thus simulating a real scenario. Finally, we use an assertion to verify that the player's score has been correctly updated to 10 points. This ensures that our game's scoring logic is functioning as intended, thus contributing to a seamless player experience during integration testing. Then we have user acceptance testing, which is perhaps the most crucial as it assesses whether your game meets the expectations of your target audience. Having real players try out the game provides invaluable feedback about game mechanics, levels, pacing, and player engagement. Encourage honest, constructive feedback. Sometimes players may find an aspect frustrating or confusing that you may not notice. As you gather feedback, you may need to pivot or make adjustments to your game design. Playtesting might reveal that your jumping mechanic feels stiff or that a level is too challenging. Adjustments made during testing are about enhancing the player's experience, ensuring that when they finally play, they're fully engaged and immersed. Now let's take a look at how we can implement a simple player damage system in Unity. The code defines a player class that inherits from monobehavior, allowing it to be attached to a game object in the Unity scene. Inside this class, we declare a public integer variable health, initialized to 100, which represents the player's starting health points. Next, we define a method called takeDamage, which takes an int parameter named damage. When this method is called, it reduces the player's health by the amount specified in the damage parameter. After updating the health, the method utilizes debug log to output a message to the console, indicating how much damage the player took and displaying their current health status. This logging is an essential feature for debugging, as it helps developers track the player's health during gameplay and identify any potential issues like unexpected player deaths. By integrating this functionality into your game, you'll be able to provide valuable feedback about the player's condition in real time, which is crucial during the testing and debugging phases of development. Now, let's see how we can implement a simple frame rate checker to monitor the performance of your game in Unity. The script begins by defining a class, frame rate checker, which extends monobehavior, allowing it to be attached to any game object in your scene. Within this class, we utilize the update method, which is called once per frame. This is an ideal place to measure the current frame rate because it runs continuously during the game's execution. Inside the update method, we use debug log to output the current frame rate to the console. The frame rate is calculated by taking the reciprocal of time delta time, a Unity property that returns the time in seconds it took to complete the last frame. This means that by logging this value every frame, you can easily keep track of how well your game is performing. By actively monitoring the frame rate, you'll be able to identify any performance bottlenecks in your game, which can help you make necessary optimizations to ensure a smoother gameplay experience. This simple yet effective tool is crucial for debugging and optimizing your game, especially when aiming for consistent performance across different devices and platforms. Finally, when all polishing, testing, and debugging have been completed, prepare your game for launch. This involves finalizing all graphics, audio, ensuring game mechanics are fluid and enjoyable, and confirming that your testing results have achieved the desired player experience. Establish metrics for success, such as player retention rates and feedback scores, to assess your game in the long term. In summary, polishing and testing are not mere afterthoughts but critical components that determine the success of your game. Engaging players through iterative testing, constant improvements in the user interface, sound design, and meticulous debugging will create a refined player experience. Embrace this stage with enthusiasm and an open mind, for the goal is to ensure your hard work culminates in a game players are excited to explore. You've put in the effort during the concept and design phases. Now is the time to enhance and optimize as you prepare for launch. Begin your journey into virtual reality development with a comprehensive introduction to the fundamental concepts, hardware requirements, and Unity environment setup. This immersive field offers many exciting possibilities for creative developers, where virtual worlds can come to life, and user experiences can transcend traditional gaming. So far, we covered the crucial final stage of game development focused on polishing and testing, which enhances the overall player experience. We discussed the significance of refining game elements, including user interfaces and sound design, and explored various testing methodologies to identify gameplay issues. Additionally, we covered debugging practices and performance testing to ensure the game runs smoothly across platforms. Lastly, we underscored the importance of player feedback in optimizing the game before its launch. Now we will dive into the core fundamentals of virtual reality development, understanding the key building blocks that will shape our VR projects. At the heart of virtual reality are two main concepts: immersion and interaction. Immersion refers to how well a user feels part of a virtual environment, while interaction allows users to manipulate and engage with that environment. Achieving high levels of both immersion and interaction involves understanding various hardware and software components essential for VR development. As we get into the technical aspects, let's first explore the hardware. The primary hardware components for developing virtual reality applications are VR headsets, motion controllers, and tracking systems. Headsets like the Oculus Rift, HTC Vive, and Valve Index provide immersive displays and sensors to track the user's head movements. Motion controllers allow users to interact with virtual objects, providing tactile feedback, which is crucial for an engaging experience. Lastly, tracking systems ensure the user's movements in the real world are accurately translated into the virtual environment. Let's consider how to set up Unity for virtual reality development. Unity is a powerful game engine that supports various VR platforms. To begin, you need to install Unity Hub, which allows you to manage different Unity versions and projects efficiently. After installing Unity, you want to create a new project with the 3D template, which provides the required setup for VR development. Once your project is created, the next step is to integrate the necessary VR SDKs. For example, if you're targeting Oculus devices, you will need to download the Oculus Integration Package from the Unity Asset Store. This package comes with predefined objects and scripts that help streamline VR development significantly. Now let's implement the following script that serves to initialize the VR settings when the game begins. This script, named VR Initializer, is attached to a game object, ensuring that the VR environment is set up properly right from the start of the game. In the script, we utilize Unity's XR management namespace to access essential functionalities for managing VR setups. The start method runs automatically when the game object is instantiated in the scene. Within this method, we call the initXR function to initialize the XR SDK that has been set up in the XR plugin management settings. This action ensures that all necessary VR devices are prepared for use. Following the initialization, we call startXR, which begins the XR SDK operation, allowing the application to start interacting with the VR hardware. By correctly implementing this script, you create a seamless entry point into the virtual environment, ensuring all VR functionalities are active and ready for player interaction. It's a fundamental step in laying the groundwork for a smooth VR experience in your project. After setting up the environment, it's essential to have a basic understanding of how to create a VR scene. Let's look at how to create a simple VR scene in Unity. Start by adding a new game object for the player. You can create an empty game object named VR Player, which will act as the parent for both the camera and the controllers. Next, proceed to add a camera to this game object. By default, Unity's main camera is not optimized for VR, so replace it with a VR camera. Find the prefab for the VR camera in the Oculus Integration Package, drag it into your scene as a child of the VR Player game object. This prefab includes everything necessary for a VR camera, including the correct scaling and interaction capabilities. Next, we will write the following script to set up the motion controllers within our VR environment. This code serves to instantiate the left and right motion controller prefabs, which are essential for player interaction in virtual reality experiences. The script begins by declaring two public game object variables, one for the left controller prefab and another for the right controller prefab. This allows us to assign specific controller models easily within the Unity editor. In addition, two private game object variables are instantiated to hold references to the actual controllers once they are created. In the start method, the script employs the instantiate function to create instances of the left and right controllers at the onset of the game. This ensures that the motion controllers are prepared for user interaction as soon as the player enters the virtual space. By attaching this script to the VR Player game object, we ensure a cohesive setup, maximizing player engagement and immersion right from the start of the scene. This straightforward yet effective implementation is a critical step in facilitating interaction within your VR application. Now let's see how we can implement basic grabbing functionality in a VR environment using Unity. The VR interactable class is designed to manage how our objects can be interacted with using a VR controller. It starts by declaring a Boolean variable is grabbable, which tracks whether the object can currently be grabbed. We utilize Unity's trigger events to determine when the VR controller enters or exits the object's collider. Specifically in the onTrigueEnter method, we check if the object entering the collider is tagged as controller. If it is, we set is grabbable to true, allowing the player to interact with this object. Conversely, in the onTrigueExit method, we revert is grabbable to false when the controller is no longer in proximity. In the update method, we check if the object is grabbable and whether the player has pressed the designated grab button. Here, you would typically implement the logic needed to perform the grabbing action. This structure creates an interactive experience, enabling players to engage with their virtual environment meaningfully. Next, it's crucial to optimize your VR experience. Performance is key when it comes to developing for VR, as the frame rate and response time can significantly impact the user's experience. Unity provides several optimization tools and techniques that can help maintain smooth performance. For instance, reducing the polygon count of the 3D models used and using occlusion culling can help reduce the overall load. Consider using the Unity Profiler to identify bottlenecks in the performance. This tool allows you to monitor the frame rate, memory allocation, and CPU usage in your scene. To access the Profiler, enable it by going to Window Analysis Profiler. From there, you can start simulating the application while profiling to see what aspects need improvement. Another common optimization is to utilize batching. Unity can batch static and dynamic objects to reduce draw calls, which has a notable impact on performance. You can enable static batching by selecting static optimization settings in the inspector while the object is selected. For dynamic objects, consider small changes in material properties or shader usage to enhance performance further without sacrificing visual quality. For example, using simplified shaders can significantly reduce overhead when rendering objects in VR. As you dive deeper into virtual reality development, user feedback becomes invaluable. Testing your VR application with real users can point out areas that require improvement that you may not notice. Engage your users, collect their feedback, and use that information to make necessary adjustments and refine your project further. Incorporating a feedback loop can also enhance user satisfaction. You can create simple feedback buttons within the VR environment, enabling users to rate their experience or report bugs. This data will be essential in further enhancing your game after its launch. Now that we have covered the basics of virtual reality development, we've laid the groundwork for building engaging and immersive experiences. We have covered essential concepts, hardware requirements, and how to set up your Unity environment. We also explored creating interactive elements and optimizing performance with user feedback. As your journey into VR continues, take these foundations and experiment with your ideas. The world of virtual reality is expansive and ever-evolving. Stay curious, keep exploring, and remember that each project enhances your skills and knowledge. In summary, we've explored the fundamentals of virtual reality development, including essential concepts of immersion and interaction, hardware components, Unity environment setup, basic scene creation, interaction implementation, and optimization techniques. Each of these elements plays a critical role in crafting a successful VR experience, and the knowledge gained in this lesson will serve as a solid foundation as you proceed to create compelling virtual reality applications. The next chapter of your development journey awaits, filled with infinite possibilities. Given the intensive resource demands of VR and AR applications, optimizing performance is important for maintaining a smooth and immersive user experience. High frame rates, minimal latency, and efficient resource use are critical to avoiding discomfort and ensuring users remain engaged in the virtual environment. So far, we learned the core fundamentals of virtual reality development, including concepts of immersion and interaction alongside essential hardware components necessary for creating VR applications. We've discussed setting up Unity for VR, covering the integration of SDKs, initial scene creation, and the implementation of motion controllers for user interaction. Additionally, we explored optimization techniques and the importance of user feedback in refining the VR experience. As we continue, we'll build upon these foundations to dive deeper into performance optimization techniques tailored for immersive technologies. Let's begin by discussing the significance of frame rates in VR. Smooth motion is critical in virtual reality. Ideally, applications must run at a minimum of 90 frames per second to create a seamless experience. Frame drops can induce motion sickness and break immersion. To ensure that your application maintains high frame rates, one common practice involves optimizing rendering processes. Unity provides several features that can help streamline rendering, such as level of detail (LOD) groups. These groups allow developers to use simpler models for distant objects while maintaining detailed models for those up close. Now let's implement the following code to set up a level of detail (LOD) group for our tree object in Unity. This code begins by defining a monobehavior class called LODExample, which will manage the LOD settings for the object it is attached to. Within the start method, we add an LOD group component to the game object, allowing us to define multiple levels of detail. Next, we create an array of LOD objects, which will hold the different levels of detail we want to assign. Here we define 3 LOD levels. The first for high detail, optimized for close views with a value of 0.5, followed by a medium detail version for mid-range distances at 0.3, and finally a low detail model for distant views at 0.1. Each LOD entry needs an array of renderers that correspond to the respective model variations. By calling setLODs, we inform Unity about the different levels of detail, and then we recalculate the bounds to ensure the group functions correctly within its defined distances. This setup enhances visual fidelity while optimizing rendering performance, crucial in VR environments where maintaining high frame rates is essential. And another vital aspect of performance optimization involves culling. Culling refers to the process of not rendering objects that are outside the camera's view, as rendering these objects wastes performance resources. Unity features both frustum culling and occlusion culling. Frustum culling discards objects that are not within the bounds of the camera frustum, while occlusion culling takes it a step further to prevent rendering objects obscured by others. To implement occlusion culling effectively, you need to bake occlusion data, which Unity uses to decide what should be rendered or culled. This process involves setting up occluders and occludes in your scene. Here is how you can enable occlusion culling in Unity. 1. Select the objects in your Unity scene that can block views. 2. In the inspector, check occluder static. 3. Go to *** window, rendering, occlusion, culling, and bake the data. Once baked, Unity can use this data to optimize rendering efficiently. Now let's talk about the use of efficient shaders. Shaders describe how to render graphics and are essential in optimizing the rendering pipeline. Complex shaders can slow down performance, making it critical to select the right shaders for your objects. Use standard shaders for most applications, and for instances where performance is paramount, consider utilizing simple surface shaders or unlit shaders that require fewer calculations during rendering. Now let's take a look at how to implement a simple unlit shader in Unity. This shader is designed to render textures without any lighting calculations, making it an excellent choice for performance-critical applications, particularly in VR. In the shader code, we first define a property called main_text, which allows us to assign a 2D texture to our shader in the Unity editor. The subshader block specifies how the shader will be rendered. Here, we mark the shader as opaque and set its level of detail (LOD) to 100, optimizing it for rendering efficiency. Next, we define a rendering pass using the CGPROGRAM directive, where we specify the vertex and fragment shaders. The appdata_t structure receives the vertex positions and texture coordinates. In the vert function, we convert vertex positions to clip space and pass the UV coordinates to the fragment shader. Finally, in the frag function, we sample the texture using the text_d function, returning the color based on the UV coordinates. This shader does not require any lighting calculations, enabling faster rendering, which is crucial in VR for maintaining high frame rates and a smooth user experience. Building on the topic of efficient resource management, graphics and texture atlasing is another optimization technique. By combining multiple textures into a single atlas, you reduce the number of separate texture calls Unity makes. This is particularly useful in VR applications where numerous objects are rendered simultaneously. Texture atlasing not only saves processing time, but also minimizes memory usage due to fewer materials being loaded. Now let's implement the following code to access a sprite from a texture atlas in Unity. This class, TextureAtlas example, demonstrates how we can utilize a sprite atlas to enhance our texture management in a VR application where performance is crucial. In this script, we first declare a public variable of type spriteAtlas. This allows us to assign a sprite atlas directly from the Unity editor, ensuring our textures are easily accessible. Within the start method, we utilize the getSprite method of the spriteAtlas class to pull a specific sprite by its name. This is where all the magic happens. Instead of loading multiple individual textures every time we want to render a sprite, we simply reference the atlas. By doing this, we improve loading times and reduce memory usage, which is essential in VR to maintain high frame rates and a smooth user experience. Thus, centralized texture management through sprite atlases not only streamlines our workflow, but also significantly optimizes performance in resource-intensive applications. Memory management is another cornerstone of performance optimization in VR applications. Because VR experiences can use significant amounts of data and require substantial hardware resources, managing memory effectively is crucial for preventing crashes and latency spikes. Efficient memory allocation practices, such as object pooling, can significantly reduce jitters and lag. Now let's see how we can implement a basic object pooling system in Unity to optimize memory usage and improve performance during gameplay. The code defines a class called ObjectPool that manages a pool of inactive objects represented by a prefab. In the start method, we instantiate a set of these objects, initially setting them to inactive and store them in a list for later use. Next, we have a method called getObject, which checks the pool for any inactive objects. If it finds one, it activates that object for use and returns it, conserving the computational resources that would otherwise be spent on instantiation. If no inactive objects are available, it simply returns null. This prevents unnecessary object creation during gameplay, which can lead to frame drops and performance issues. Finally, the returnObject method allows us to deactivate an object when it's no longer needed, returning it to the pool for future use. This efficient management of memory ensures that we minimize overhead, providing a smoother experience, particularly critical in VR applications where performance is paramount. Finally, let's cover the importance of profiling tools in performance optimization. Unity includes a powerful profiler that tracks various metrics, including CPU, GPU rendering times, memory usage, and more. Using this tool helps you understand where bottlenecks occur in your application. When profile sessions are running, you'll gain insights into how different aspects of your scene contribute to the overall performance. To use the Unity Profiler, navigate to *Window Analysis, Profiler *, and start a profiling session. You'll be able to inspect the various functions and understand which parts of your code demand the most resources. Look for spikes in CPU usage during gameplay and address bottlenecks through optimization strategies discussed earlier. As we conclude this discussion on performance optimization techniques for immersive technologies, remember that efficiently managing frame rates, rendering processes, memory usage, and shader complexity is essential for enhancing user experience within VR and AR applications. Profiling your application and utilizing tools provided within Unity can make a significant difference in achieving high performance while delivering an engaging experience. We've covered several performance optimization strategies today: LOD groups, culling, efficient shaders, texture atlasing, object pooling, and the importance of profiling. By implementing these techniques effectively, you'll create immersive virtual environments that feel smooth and responsive to users, enhancing their overall experience. So keep pushing the boundaries of your VR creations and happy developing. Cross-platform game development in Unity presents unique challenges and opportunities. As the gaming industry expands, it's crucial to master the art of creating games that excel on mobile, desktop, and console platforms. This video will guide you through the intricacies of cross-platform development, offering strategies to optimize performance, design versatile user interfaces, and manage resources efficiently. So far, we covered the importance of optimizing performance in VR and AR applications, exploring techniques such as level of detail LOD groups and effective resource management. Now we will dive into cross-platform game development, discussing various challenges, strategies, and best practices that will help you create scalable and high-performing games across multiple platforms. Now let's see how we can enhance our game's texture management with efficient MIP mapping and dynamic quality adjustments. In this script, we create a Texture Manager class that handles loading and applying textures based on the device's performance capabilities. Upon starting the game, the start method sets the filter mode of the texture to trilinear, which improves visual fidelity by allowing smooth transitions between MIP map levels. In the update method, we implement a simple check to assess the current quality level of the game. If the quality level falls below a certain threshold, an indicator that the device may not be able to handle high-quality assets, we dynamically load a lower-resolution texture using the Load Low-Quality Texture method. This method accesses a specified file path to retrieve a lower-quality texture, ensuring that our game maintains adequate performance, especially on mobile devices with limited resources. By adapting texture quality in real time, we can enhance the gaming experience for users on various platforms while effectively managing device resources. Now let's take a look at how to handle player movement, specifically the jump action in Unity. In this code, we define a player controller class that inherits from mono behavior, allowing it to integrate seamlessly with Unity's game loop. We declare a public variable jumpForce to set the strength of the jump and a private variable RB for tracking the player's rigid body. During the start method, which runs once at the beginning of the game, we initialize our RB variable by fetching the rigid body component attached to the player object. This component is essential for applying physics-based movement, such as jumping. In the update method, we check for the jump input using Unity's input system. This input action is mapped to various control schemes, ensuring that a player can jump regardless of whether they are using a touchscreen, gamepad, or keyboard. If the jump condition is met, we apply an upwards force to the player's rigid body. This implementation exemplifies how to unify control schemes across platforms while maintaining a consistent and engaging gameplay experience. Now let's implement the following UI Manager script that utilizes Unity's Canvas Scaler component to create adaptable user interfaces. In this script, we begin by defining a public variable for the Canvas Scaler, which allows us to configure it directly from the Unity inspector. In the start method, we set the Canvas Scaler's UI Scale mode to Scale with Screen Size, which enables the UI elements to scale proportionally based on the screen dimensions. This ensures that no matter the size of the device, the UI remains visually consistent and user-friendly. Furthermore, we establish a reference resolution, which in this case is set to 1920 by 1080, a common full HD resolution. This reference acts as a baseline for scaling other dimensions. The match-width-height property is set to 0.5, indicating that the scaling will place equal importance on both the width and height, making the UI more versatile across different aspect ratios. Finally, we have an Update UI method where you can add code to dynamically reposition UI elements as needed, reinforcing the adaptability and responsiveness of your interface design across various platforms. This practice enhances user experience by keeping the UI elements properly aligned and easily readable, regardless of the device used. Now let's take a look at an implementation for dynamically loading game assets in Unity. This approach is particularly beneficial for mobile game development, where loading all assets at once can lead to excessive memory usage and slow performance. In this script, we define a class called AssetLoader, which inherits from mono behavior. We'll start by declaring a public string variable, AssetPath, which holds the path to our assets folder. This allows for flexibility in loading different assets based on the provided path. Next, we implement a method named loadAsset, which takes an asset name as a parameter. Within this method, we utilize Unity's resources load function to fetch the desired asset from the specified path. The loaded asset is of type GameObject, making it ready for instantiation into the scene. Finally, we instantiate the loaded asset, returning it to be placed in the game world. This method efficiently manages memory by loading assets only when needed during gameplay, enhancing overall performance on mobile devices. By integrating this dynamic loading pattern, we ensure that our game remains responsive and lightweight, addressing the unique challenges posed by mobile platforms. Now let's implement a simple unit test to verify that our player's jump action works as intended. In this example, we create a new game object that represents the player and attach our player controller script to it. This setup enables us to test the jump functionality in controlled conditions. We begin by setting the jump force property to a value of 5F, which determines the force applied to the player during a jump. We then store the player's original vertical position, allowing us to measure any changes after the jump action is executed. Next, we call the update method of the player controller, which handles the input for the jump. A yield statement is used to pause the execution until the next frame, simulating real-time behavior in the game. Finally, we assert that the player's new vertical position is indeed greater than the original position. If this condition is met, the test passes, confirming that the jump functionality is correctly implemented. Incorporating such automated tests not only enhances code quality, but also ensures consistency across updates and modifications in the game's lifecycle. Lastly, let's discuss how to enrich the user experience and interface across various platforms. It's vital not only to create responsive designs, but also to ensure that your game is accessible to all potential players. This includes implementing high-contrast visuals, legible fonts, and adaptable input methods that cater to different user needs. When designing for accessibility, you can incorporate guidelines such as using text color that contrasts strongly against the background, ensuring that text is large enough to read easily without straining, allowing players to navigate the game without hindrance, regardless of the input method used. Adopting these practices not only improves usability but also broadens your game's audience, enhancing its reach and reception. In conclusion, cross-platform game development requires careful planning, innovative problem-solving, and adaptability to meet the various challenges posed by different devices. By leveraging Unity's robust tools and employing flexible strategies for performance optimization, input management, responsive UI design, and diligent testing, you can create engaging and high-quality games that run seamlessly across mobile, desktop, and console platforms. As we wrap up this segment, remember that mastering these principles will put you on the path to successfully delivering captivating gaming experiences to a diverse audience. Stay tuned for our next lesson, where we will explore effective strategies for publishing and monetizing your game. Let's embark on the crucial final stages of your game development journey with Unity as we delve into publishing, monetizing, and marketing your game. This video will ensure that you are well equipped with various strategies to navigate the complex landscape of game publishing and marketing to guarantee success in reaching your audience. So far, we learned about the critical aspects of cross-platform game development in Unity, including the importance of optimizing performance for varying hardware specifications among devices. We've explored techniques for dynamic asset management, responsive UI design, and supporting diverse input methods to enhance user experience. Additionally, the significance of thorough testing across different platforms and adhering to accessibility guidelines was emphasized. As we move forward, we'll delve into effective strategies for publishing and monetizing your game. Now let's take a look at how to set up a script in Unity that allows you to build your game for specific platforms, namely Steam and the App Store. This script, named Game Build Settings, utilizes the Unity Editor scripting feature to create custom menu items in the Unity Editor. First, we define two methods, each marked with the menu item attribute, which registers them in the Build menu panel of the Unity Editor. The first method, Build for Steam, compiles the specified game scene into a standalone executable for Windows, directing the output to the Steam folder. Here we use the build pipeline, build player method with parameters detailing the scene path, output file, target platform, and build options. A debug log statement confirms the completion of the build process. Similarly, the second method, build for App Store, handles the building process for iOS by generating an Xcode project. By utilizing the same build pipeline, build player function with appropriate arguments for the iOS platform, this method streamlines your submission process. Together, these methods ensure that your game can be efficiently prepared for release on both platforms, highlighting the importance of custom build processes in Unity development. Now let's see how we can implement in-app purchases (IAPs) in Unity to enhance the gameplay experience for players. The script begins by initializing the IAP system in the Unity environment using the configuration builder class. When the game starts, the start method is called, which sets up the necessary configuration for handling purchases. Specifically, it adds a consumable product called MyGameCoins, allowing players to buy in-game currency that they can use during gameplay. Next, we introduce a method called BuyCoins, which serves to initiate the purchase process when a player decides to buy coins. Within this method, we invoke the BuyProduct function with the corresponding product ID. This function checks if the product is available for purchase by accessing the product catalog. If it is available, the purchase is then processed through the purchase service. This setup is crucial for creating a balanced in-game economy, as it allows users to acquire virtual goods without overwhelming their experience. Successful implementation of these purchases can lead to increased player engagement and satisfaction. Now let's implement the following script to integrate Unity ads into your game, utilizing various ad formats to enhance monetization while keeping gameplay smooth. The Ad Manager class begins by defining necessary parameters, including your Unity ads game ID and a toggle for test mode, which is essential for testing your ad implementations without affecting real metrics. Within the start method, we initialize Unity ads using the provided game ID and test mode setting, ensuring that our game is ready to load ads when it starts. Next, the show_rewarded ad method is where the core functionality lies. This function checks if a rewarded video ad is ready to be displayed by calling advertisement is ready, and if it's available, it uses advertisement show to present the ad to players. It's crucial to integrate ad placements thoughtfully to maintain player engagement, ensuring that advertisements enhance rather than disrupt the gaming experience. By strategically incorporating rewarded video ads, you provide players with incentives, creating a win-win scenario for both your monetization efforts and player satisfaction. Now that we've covered monetization, it's time to shift focus to marketing, an indispensable aspect of ensuring that your game reaches its audience. Developing a compelling marketing strategy begins with creating high-quality promotional materials such as trailers and images. A well-crafted trailer captures the essence of your game and entices potential players. Another great way to gather interest is by posting regular development updates to engage your audience. Here's a quick tip on how to structure your game trailer. 1. Engaging gameplay footage ***. Focus on showcasing your game's most exciting moments. 2. Captivating music ***. A powerful soundtrack can add emotional weight to your visuals. 3. Clear call to action. Encourage viewers to follow your game or visit your website for more details. You may consider the inclusion of press kits for journalists and influencers, which should contain high-resolution images, game descriptions, and key features. Now let's see how we can implement an automated response system for social media comments using C#. This is achieved through a simple class named Social Media Manager, which utilizes a hypothetical Twitter API to engage with users directly. The call function, respond to comments, takes a string parameter representing the comment. Inside this method, we utilize a conditional statement to check if the comment contains the term excited. If this condition is met, it triggers a response that acknowledges the user's enthusiasm. Specifically, the code makes use of the post-reply method from the Twitter API to send a tailored message to the user. This approach allows you to maintain an active social media presence by automating responses to positive engagement. It's a strategic way to connect with your audience and encourage them to stay interested in your game. By employing such automated strategies, you can save time on individual responses while still fostering a sense of community and keeping your followers engaged. Building and nurturing a community around your game is essential for longevity. Engage directly with players via forums and Discord servers, encouraging discussions and hosting events. This interaction fosters a loyal player base and makes them feel valued as part of your game's journey. Establishing clear community guidelines prevents toxicity and ensures that your gaming environment is welcoming. Utilize comprehensive tools such as Discord bots or community moderators to assist with this. Regularly seek feedback through surveys to understand your players' experiences and perspectives. In summary, the process of publishing, monetizing, and marketing your game is intricate but rewarding. With an informed approach to selecting the right platforms, implementing effective monetization strategies, and engaging in thorough marketing efforts, you can set your game up for success. Your journey through these stages will ensure that you not only launch your game effectively, but also cultivate a community that supports and enjoys your work. Stick with it, and you'll see your game flourish in the competitive market.